Welcome to this course about computer networks and network security. According to Fortune Business Insights, the global network as a service market size is forecast to grow from $18.7 billion to $155.17 billion by 2030, showing a compound annual growth rate of 35.3%. Take this hands-on IBM course to develop or start a new network or network security career, are a graduate seeking to establish new network skills, or are an IT supervisor who wants a deeper understanding of their team's work. Gain knowledge and skills through instructional videos, hands-on labs, practice, graded quizzes, valuable reference materials, and a real-world final project. In this course, you'll learn about networking ports and protocols through videos and labs. You'll learn about the IP address structure, including IPv6 addresses and network classes. You'll gain fundamental knowledge of network routing concepts and practices, learn about the relevant differences between Layer 2 and 3 network addressing, and gain the knowledge needed to explain and work with routers and routing tables functions and configurations. You'll also learn how organizations use intrusion detection and prevention systems for endpoint and extended detection and protections, and gain insight into how these systems fit into an organization's overall network security structure. You'll complete this course with practical, hands-on experience identifying networking ports and protocols. You'll also gain expertise in securing a small home office network called the Soho Network. Then, you'll learn how to install and configure a dynamic host configuration protocol, DHCP. Then, you'll gain job-ready skills performing DNS filtering using Windows Defender Firewall and carrying out intrusion detection system activities. Then, you'll gain valuable real-world skills using open-source Extended Detection and Response, XDR systems. The final module includes a practical, hands-on project where you'll provide network design and security configuration recommendations for a new branch office network. You will find it helpful to be familiar with Microsoft Windows, Linux, or Mac OS operating systems, and proficient in the command line interface. This course is foundational knowledge for the IBM Cybersecurity Analyst Professional Certificate, crafted to help you attain an entry-level cybersecurity role. There's a lot to learn. To get the most from this course, watch each video, complete all hands-on labs, and check your learning with each quiz. We're delighted to accompany you as you learn about network and network security. If you have trouble with the course material, please get in touch with us in the discussion forum. Let's get started.
Welcome to Computer Networks, Networking Hardware Devices. After watching this video, you will be able to identify common networking hardware devices, list differences between similar network devices, and explain the significance of each type of network device and its functions. Network devices, or networking hardware, are physical devices that enable communication and interaction on a computer network. This includes cables, servers, desktops, laptops, tablets, smartphones, and Internet of Things, or IoT devices. This video covers network devices that connect or route, such as hubs, switches, routers, bridges, and gateways. A server is a powerful computer that stores files and applications. Other computers or devices on the same network can access the server as a central place to store information or use applications. The devices that access the server are known as clients. The server controls the level of access that clients have. A user can access a server file or application from anywhere if they use a client that is connected to the server's network and has the proper level of access, usually password-based. A node is a network-connected device that can send or receive information. A client is a node that accesses the network through a server. All devices that can send, receive, and create information on a network are nodes. The nodes that access servers to get on the network are known as clients. The server controls the level of access that clients have. If a client fails, the network remains unchanged. Client-server networks are common in businesses. They keep files up to date and easy to find by ensuring users work on one shared file in one location. Examples of services that use client-server networks include file transfer protocol sites, or FTP sites, web servers, and web browsers. Peer-to-peer networks are common in homes and on the Internet. Peer-to-peer networks allow users to share resources and information. Examples include file-sharing sites, discussion forums, media streaming, and voice-over IP services, also called VoIP services. A hub connects multiple devices together in a network. When data is sent to a hub, it broadcasts that data to all devices on the network, except for the one that sent the data. A switch is similar to a hub, except it keeps a table of MAC addresses. When a switch receives any data, it looks up the proper MAC address and forwards the data to the right place. Switches are more efficient than hubs because they only send data to the intended recipient. Switches and hubs connect to modems. If a switch or a hub fails, it brings the entire network down. Routers interconnect different networks or subnetworks. A router serves two primary functions. They manage traffic between networks by forwarding data packets to their intended IP addresses, and they allow multiple devices to use the same internet connection. Routers connect to modems. To direct packets effectively, a router uses an internal routing table, which is a list of paths to various network destinations. The router reads a packet's header to determine its path, consults the routing table to figure out the most efficient path, then forwards the packet to the next network in the path. A modem, or modulator-demodulator, converts data into a format that is easy to transmit across a network. Once that data reaches its destination, the receiving modem converts it back to its original form. The most common modems in use today are cable and DSL modems. A bridge joins two separate computer networks so they can communicate with each other and work as a single network. Bridges can be wired or wireless. Wireless bridges can support Wi-Fi to Wi-Fi, Wi-Fi to Ethernet, and Bluetooth to Wi-Fi connections. A gateway is hardware or software that allows data to flow from one network to another. For example, a home network to the Internet. Gateways are distinct from routers or switches in that they use multiple protocols to connect multiple networks. A repeater, or extender, receives a signal and retransmits it. Repeaters are used to extend a wireless signal so it can cover longer distances or be received on the other side of an obstruction like brick, steel, or concrete. Repeaters connect to wireless routers. A wireless access point, also known as WAP or AP, allows Wi-Fi devices to connect to a wired network. The WAP usually connects to a wired router as a standalone device. The WAP can also act as a central wireless connection point for computers equipped with wireless network adapters. The WAP is plugged into a wired network switch. The WAP reads each computer's MAC address and forwards that to the wired switch. If the wired network is connected to a router with Internet access, the wireless network will also have Internet access. Network interface cards, or NICs, connect individual devices to a network. NICs can be wired or wireless. Today's computers usually come with wireless NICs already built in. Most include ports for network cables, so users can easily connect their computer to a network. A firewall monitors and controls incoming and outgoing network traffic based on predetermined security rules. A firewall typically establishes a barrier between a trusted internal network and untrusted external network, like the Internet. Firewalls can be either software or hardware. Wireless routers and computer operating systems often have built-in firewalls. A proxy server acts as an intermediary between a LAN and the Internet to minimize security risks. The proxy server evaluates requests from clients and forwards them to the appropriate server if those requests meet preset security requirements. Proxy servers hide an IP address. If an IP address is hidden, it cannot be tracked. Proxy servers save bandwidth. For example, a proxy server will download files or updates for the first user, then keep them stored for any future users who need them. An intrusion detection system, or IDS, monitors network traffic and reports malicious activity to the network administrator. An intrusion prevention system, or IPS, inspects network traffic and removes, detains, or redirects malicious items based on rules set by the network administrator. In this video, you learned network devices, which can be a variety of different types, enable communication and interaction on a network. Servers are powerful computers that store files and applications. and are accessed by other computers on the same network. Nodes and clients can be configured in different ways. Routers and modems transmit and convert data to ensure interconnections happen and information reaches its destination correctly. And firewalls, proxy servers, IDS, and IPS work to keep networks secure. Welcome to Computer Networks, Models, Standards, Protocols, and Ports. After this video, you will be able to explain networking models and standards, list the role of each protocol type, and define common ports. A networking model describes the architecture, components, and design used to establish communication between the source and destination systems. Data packets follow the protocols of network models. There are two types of networking models. The OSI, or Open Systems Interconnection Model, is a conceptual framework used to describe the functions of a networking system. The TCP/IP, or Transmission Control Protocol Internet Protocol Model, is a set of standards that allow computers to communicate on a network. TCP/IP is based on the OSI model. The OSI model is a conceptual framework used to describe the functions of a networking system. Data flows across these layers when communicating over a network. The 7 layers of the OSI model include application. Users and applications interact directly with the software application. Presentation. Ensures that data is in a usable format and is where data encryption occurs. Session. Controls the flow of information between different computers, including authentication and reconnections. Transport. Manages the delivery and error checking of data packets. Data is commonly transported using Transmission Control Protocol, or TCP. Network. Responsible for interpreting the addresses and directing the path the data will take. Data link. Defines the format of data on the network. This layer also corrects errors that may have happened at the physical layer. And physical. Electrically or optically transmits raw, unstructured data over a physical medium. The TCP/IP model is a set of standards that allow computers to communicate on a network. TCP/IP is based on the OSI model and functions similarly. The background protocols are still in place, but the way they are organized is slightly different. The data travels through fewer layers on both ends. Networking standards define the rules for data communications that are needed for interoperability of networking technologies and processes. Standards are widely accepted protocols that engineers use to make sure the things they build integrate with existing devices and technology. There are 2 types of network standards. De jure, or formal standard, are formal standards developed by an official industry or government body. Formal standards have gone through formal processes to obtain consensus, including publicly available documentation. Examples include HTTP, HTML, IP, and Ethernet 802.3d. De facto standards result from marketplace domination or practice. De facto standards are accepted in practice but have not undergone any formal process to obtain consensus and may not have publicly available documentation. Typically, de facto standards result from marketplace domination or practice. Examples include Microsoft Windows and QWERTY keyboard. Standards are usually created by government or nonprofit organizations for the betterment of an entire industry. This ensures a broader compatibility across vendors and industries. Some of the well-known organizations that have created network standards are International Standards Organization, or ISO, established the well-known OSI reference networking model. International Telecommunication Union, or ITU, standardized international telecom and set standards for fair use in radio frequency. Defense Advanced Research Projects Agency, or DARPA, established the TCP/IP protocol suite. Institute of Electronics and Electrical Engineers, or IEEE, established the IEEE 802 standards. The World Wide Web Consortium, or W3C, established the World Wide Web, WWW, standard. Finally, the Internet Engineering Task Force, or IETF, maintains the TCP/IP protocol suites. IETF also developed the Request for Comment, or RFC, standard. A network protocol is an established set of rules that determine how data is transmitted between different devices in the same network. Network protocols are typically created according to industry standards. There are thousands of different network protocols, but they all perform one of three primary actions: security, communication, and network management. Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP, are two primary Internet protocols. TCP guarantees sent data makes it to its intended recipient. It's slower and requires more resources. File Transfer Protocol, or FTP, web browsing, and email are typical applications of TCP. UDP doesn't guarantee all packets will arrive, but it's fast and needs fewer resources, good for live streaming, online gaming, and calls over the Internet. The TCP IP suite is a collection of protocols. Together, these protocols provide a complete networking solution. The Internet of Things, or IoT, network model comprises diverse protocols for communication, which include data collection, data package, data transfer, and data control. The Crypto Classic protocol is designed to serve as one of the most efficient, effective, and secure payment methods built on the blockchain network. It ensures privacy and transparency of payments directly transferred between two parties who have an address on the blockchain network. Ports are the first and last stop for information sent across a network. A port is a communication endpoint. A port always has an associated protocol and application. The protocol is the path that leads to the application's port. A network device can have up to 65,536 ports. Port numbers do not change.
A socket is a two-way communication channel. Each socket is made up of a source IP address, a protocol, a port number, a destination IP address. You use a socket whenever you send data over your local network or over the Internet. For example, whenever you use a web browser, send an email, or watch a video online, a socket is used over the network in order to make that communication possible. In this video, you learned that network models in OSI and TCP IP describe the design used to establish network communication. Network standards define the rules for data communication and ensure broader compatibility. Network protocols are based on an established set of rules for data transmission. Sockets use ports and protocols to facilitate communication between network devices.
Welcome to Computer Networks, Wireless Networks and Standards. After watching this video, you will be able to explain the different wireless network types, list the advantages and disadvantages of each wireless network type, and describe the wireless networking standards. As an alternative to traditional cable and fiber optic networks, wireless networks have become crucial for enabling mobility. Wireless networks like WPAN, WLAN, WMAN, and WWAN use radio waves for data transmission and reception instead of wires. And they follow IEEE wireless standards. These are the sets of protocols that define how all wireless communication works. This video describes how wireless networks function and what each one is used for. A WPAN connects devices within the range of an individual person, around 10 meters. WPANs use signals like infrared, Zigbee, Bluetooth, and ultra-wideband. WPANs use the IEEE 802.15 wireless standard. Bluetooth and Zigbee are some of the IEEE 802.15 signals that wirelessly connect devices over short distances. Advantages include flexible and efficient, one-time easy setup, and portable. Disadvantages include limited range, limited data rates, and more expensive. A WLAN connects computers and devices within homes, offices, or small businesses. WLANs use Wi-Fi signals from routers, modems, and wireless access points to wirelessly connect devices. Wi-Fi follows the IEEE 802.11 wireless standard. The latest version of IEEE 802.11ax enables 8K video streaming, data-heavy cloud computing, and virtual reality experiences. Advantages include reliable and versatile, high data transmission rates, and easy to manage. Disadvantages include low network coverage area, number of devices affects speed, and less secure. A WMAN spans a geographic area. It serves ranges greater than 100 meters. Worldwide Interoperability for Microwave Access, or WiMAX, is a family of wireless communication standards that provide WMAN broadband connectivity. There are similar open-source and proprietary broadband technologies, but WiMAX is the accepted suite of standards based on IEEE 802.16. Advantages include covers multiple city locations, easy to use, extend, and exchange, and managed by an ISP, government entity, or corporation. Disadvantages include requires special user permissions, less secure, and slower than wired. A WWAN provides regional, nationwide, and global wireless coverage. This includes private networks of multinational corporations, the Internet, cellular networks like 4G, 5G, long-term evolution, or LTE, and LoRaWAN, which is a low-power WAN protocol built on top of the techniques used in long-range radio modulation. Advantages include global wireless coverage, better security than WLAN, and centralized flexible infrastructure like cloud apps and storage. Disadvantages include expensive, difficult to maintain, and decreased coverage over large areas. A wireless ad hoc network, or WANET, uses Wi-Fi signals from whatever infrastructure happens to be available at the time to connect devices instantly, anywhere. WANETs are similar in size to WLANs, but use technology that is closer to WWANs and cellular networks. Advantages include flexible, no required infrastructure, and can be set up anywhere instantly. Disadvantages include limited bandwidth quality, not robust, and has security risks. There are also MANETs, or mobile ad hoc networks, and VANETs, or vehicle ad hoc networks. These are similar to WANETs but have different specifications. A cellular network provides regional, nationwide, and global mesh coverage for mobile devices. Each version below represents a cellular network evolution. 2G supported digital voice and simple data with 64 kilobits per second speed. 3G supported mobile broadband with 2 megabits per second speed, which enabled basic GPS, media downloads, and streaming. 4G advanced speeds and efficiencies with 100 megabits per second speed. And 5G brought 1 gigabits per second speed, which is still bringing cellular networks to a whole new level. Advantages of cellular networks include flexibility, access, and speed and efficiency as it evolves. Disadvantages include expensive, decreased coverage in rural areas, and hardware limitations, like screen size and mobility of peripherals. The IEEE 802.20 and IEEE 802.22 network standards support WWANs, cellular networks, and WANETs. Well-known use cases include emergency mobile operations, internet on airplanes, internet service provider networks, and large-scale monitoring for things like earthquake zones, flood warnings, and space exploration. IEEE 802.20 uses smart antennas to optimize bandwidth for increased coverage or mobility. It is no longer being actively developed, but it is still used to fill the gap between cellular and other wireless networks. IEEE 802.22 uses empty spaces in the TV frequency spectrum to bring broadband to low-population, hard-to-reach areas typical of rural environments. In this video, you learned that WPANs use IEEE 802.15 for nearby devices. WLANs use IEEE 802.11 for home or office networks. WMANs use IEEE 802.15 for city or campus networks. WWANs supply regional or global networks. WANETs are LAN-sized temporary mobile networks. Cellular networks have evolved over time to become faster and more efficient. And IEEE 802.20 and 802.22 are the standards for WWANs, WANETs, and cellular networks.
Welcome to Protocol Table. After watching this video, you will be able to explain the difference between TCP and UDP, describe the relationship between ports and protocols, and list common protocols and their uses. A network protocol is an established set of rules that determine how data is transmitted between different devices in the same network. Network protocols are typically created according to industry standards. There are thousands of different network protocols, but they all perform one of three primary actions: security, communication, and network management. Ports are the first and last stops for information sent across a network. A port is a communication endpoint. A port always has an associated protocol and application. The protocol is the path that leads to the application's port. A network device can have up to 65,536 ports. And default port numbers do not change. Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP, are two primary Internet protocols. TCP guarantees that sent data makes it to its intended recipient. It's slower and requires more resources. Typical applications include File Transfer Protocol, or FTP, web browsing, and email. UDP doesn't guarantee that all packets will arrive, but it's fast and requires fewer resources. Typical applications include live streaming, online gaming, and calls over the Internet. Ports send and receive data using TCP, UDP, and sometimes both. Web page protocols control access and connection between Internet users and the sites they visit. Hypertext Transfer Protocol, or HTTP, is responsible for standard Internet or web page access. The default port for HTTP is 80. And Hypertext Transfer Protocol Secure, or HTTPS, is responsible for encrypted Internet or web page access. HTTPS should be used on a web page that prompts for sensitive data, such as credit card numbers. The default port for HTTPS is 443. File transfer protocols control how data is managed when sent from one location to another. File Transfer Protocol, or FTP, is responsible for file transfer. FTP transfers files to and from an FTP server or client. The default port for FTP is 21. And Secure File Transfer Protocol, or SFTP, is responsible for encrypted file transfer. The default port for SFTP is 22. Remote access protocols enable device control from a remote location. Teletype network, or Telnet, is used to remotely control another device via console or command shell. Telnet lets users configure network devices from almost anywhere worldwide, so long as both devices have network connectivity. However, Telnet should not be used due to data being in clear text, no encryption. The default port for Telnet is 23. Secure Shell, or SSH, is used to remotely control another device via console or command shell securely with encryption. SSH uses encryption to secure remote data. The default port for SSH is 22, which is the same port that SFTP uses, since they both offer similar secured services. And Remote Desktop Protocol, or RDP, is used to remotely control another computer via a graphical user interface, also called GUI or GUI for short. Email protocols determine how email messages are received, stored, downloaded, removed, or retained. Post Office Protocol version 3, or POP3, is an older protocol that was the standard for receiving email. With POP3, email is downloaded from an email server to a single device, and then the email is deleted from the server. The default port for POP3 is 110. Internet Message Access Protocol version 4, or IMAP4, is a protocol responsible for receiving email. With IMAP4, email is stored on the server and synchronized to multiple devices, like laptops and mobile phones. The default port for IMAP4 is 143. And Simple Mail Transfer Protocol, or SMTP, is responsible for sending email. The default port for SMTP is 25. Network protocols monitor, control, and help the network locate, share, and transfer data. Dynamic Host Configuration Protocol, or DHCP, automatically assigns IP addresses to devices. The default ports for DHCP are 67 and 68. Domain Name System, or DNS, resolves or translates domain names to IP addresses. The default port for DNS is 53. Server Message Block, or SMB, enables sharing files and printers on the network. The default ports for SMB are 137 through 139. Simple Network Management Protocol, or SNMP, monitors the network. The default port for SNMP is 161. And Lightweight Directory Access Protocol, or LDAP, allows directory services to store and authenticate passwords, usernames, and accounts and share them over the network. The default port for LDAP is 389. In this video, you learn that protocols determine how data flows on a network. Ports are the first and last stops on a network. Ports send and receive via TCP, UDP, or both. HTTP and HTTPS are web page protocols. FTP and SFTP are file transfer protocols. Telnet, SSH, and RDP are remote access protocols. POP3, IMAP4, and SMTP are email protocols. And DHCP, DNS, SMB, SNMP, and LDAP are network protocols. Welcome to the Microsoft Windows Server Lab environment. After watching this video, you'll be able to navigate the Windows Server Lab, simulate real-world server management tasks, sweep between instructions and server panels, and apply practical knowledge while understanding the variations in Windows Server editions. You'll also be prepared to complete tasks within temporary lab sessions and use tools like the on-screen keyboard when needed. Now imagine being in charge of configuring a server for a large organization. That's what this lab environment offers, a safe place to explore and manage Windows Server features without any risk to a live environment. To get started, access the lab by agreeing to the honor code and clicking Launch App. Once the lab loads, you'll see two sections: the left panel with instructions and the right panel with the Windows Server environment, where you'll perform your tasks. If you prefer, you can swap the positions of these panels by using the switch arrow in the middle of the screen. The lab might take 2 to 3 minutes to fully load, so be patient while the environment initializes. Remember that features in the Windows Server environment may differ based on the edition being used. If you're practicing on a local machine, some solutions might vary from those in the lab. If you run into trouble with your physical keyboard, no worries. You can use the on-screen keyboard by searching for it in the search bar. If the search function isn't working, you can access it through Windows Ease of Access in the Start menu. Lastly, remember that each lab session is temporary. Make sure to complete your tasks in one session, since anything saved won't carry over to the next. Let's recap. In this video, you've learned how to access and navigate the Windows Server Lab environment, swap between panels, use the on-screen keyboard, and handle temporary lab sessions. You've also learned to account for differences in Windows Server editions when practicing on your local machine. You're now ready to explore and apply your server management skills. Welcome to IP Addressing, the basics of binary. After watching this video, you'll be able to discuss number systems, convert number systems, and calculate the range of numbers in different base systems. With the increase in data exchange, IP addresses are continuously monitored to detect suspicious activity within a network. An IP address is represented as a dotted decimal number that involves binary numbers with a base 2. These binary numbers can be converted to octal, decimal, and hexadecimal number systems with bases 8, 10, and 16 respectively, also called representation numbers. The most used base is 10, which is known as the decimal number system. The base 10 system was widely used as it was easier to calculate with 10 fingers and 10 toes. Remember, decimal means 10. Here, each digit is worth 10 times as much as the preceding digit and can hold values ranging from 0 through 9. Whereas the binary system, base 2, is where computers only know two different states, that is, on and off, high voltage and low voltage, or open gate and closed gate, which is represented logically as 1 or 0. There are digits for 1, tens, hundreds, thousands, 10,000s, etc., where each digit is worth 10 times as much as the preceding digit. Usually, the placeholders in the binary system represent 1s, 2s, 4s, 8s, 16s, etc., doubling each time. Here each digit is worth 2 times as much as the preceding digit. Now, let us understand how to convert binary numbers to decimal. To convert from binary to decimal, you just need to add up all the values of the digits that contain 1 and ignore those that contain zeros. Let's take an example. Shown here is an 8-digit binary number, which means there are 8 placeholders. So, if the binary number is 110111010, then it would convert to decimal as 2 plus 8 plus 16 plus 64 plus 128, which is equal to 218. Now let's understand how to convert decimal to binary. To convert decimal to binary manually, first, identify the largest binary placeholder that can be subtracted from the decimal number. Next, subtract this value, place a 1 in that placeholder, and continue with the remainder. Let's take an example to understand this better. Take the number 235. To convert 235 from decimal to binary, first, identify the largest binary placeholder that you can subtract from the decimal number. Since here 256 is too large, you can subtract the next smaller placeholder, which is 128, as shown. Now, put a 1 in the 128th place, and then subtract 128 from 235. The answer is 107. Since 107 is greater than 64, you can subtract 64 from 107. Add 1 to the 64 placeholder, and subtract 64 from 127, leaving the answer 43. Check the next placeholder down, if 32 can be subtracted from 43. Yes. Now, add 1 to the 32 placeholder and subtract it from 43, leaving the answer as 11. For the next step, check the next placeholder down, if 16 can be subtracted from 11. Since 16 is greater than 11, put a 0 in the 16 placeholder and check the next placeholder down. Now, since 8 can be subtracted from 11, let's put a 1 in the 8 placeholder and subtract 8 from 11, leaving an answer of 3. Repeat the steps till you get the answer 1 and the next placeholder is 1. Now subtract this one from 1 and put a 1 in the placeholder and subtract. 1 minus 1 is 0. Voila! Here is your answer. 235 in binary is 111011011. In addition to binary and decimal number systems, octal and hexadecimal systems are widely used in a few instances. Let's discuss them. The octal is base 8. It is less common than primary and can take on 8 possible values ranging from 0 to 7, whereas the hexadecimal, also called hex for short, is base 16. It can take on 16 possible values ranging from 0 to F. Note that in a hexadecimal system, after you reach 10, you can start using letters. Hence, numbers 10 through 15 are represented by A, B, C, D, E, and F, respectively. Let's understand how to calculate number representations. For any number system, you can calculate the representations by simply raising the base you're working with to the power of the number of digits available. Let's understand this with an example. In binary, you raise 2 because it's base 2 to the power of 4, and thus get 16 different numbers that are represented using these 4 digits. Since 0 counts as a possible number, that would give you a range of 0 through 1111 or 0 through 15. In octal, raise the base 8 to the power of 4 and get 4,096 possible numbers. That would give you a range of 0 through 7,777. That's 0 to 4,095 in decimals. Similarly, in decimal, 10 raised to the 4th power is 10,000, which gives you a range of 0 through 9,999. Finally, in hex, the largest number would be 16 raised to the 4th power, or 65,536 in decimal. That would give you a range of 0 to F, or 0 to 65,535 in decimal. Let's now discuss how to convert between number systems. To convert from any base system to decimal, draw a table where column headers represent the base raised to increasing powers, that is 0, 1, 2, 3, etc. For binary, that would be 1, 2, 4, 8, etc. Similarly, for octal, that would be 1, 8, 64, 512, etc. And for decimal, that would be 1, 10, 100, 1000, etc. And for hex, it would be 1, 16, 256, and 4096, etc. In this video, you learn that decimal operates on base 10, while binary operates on base 2. Hexadecimal, base 16, offers a more compact number representation compared to binary. To calculate the number representations, raise the base to the power of the number of digits available. To convert from any base system to decimal, draw a table where column headers represent the base raised to increasing powers. Welcome to IP address structure and network classes. After watching this video, you will be able to explore the 4-octet format of IPv4 addresses, discuss the characteristics of Class A, B, C, D, and E networks, convert IPv4 addresses between decimal and binary, and list the limitations of IPv4. While setting up a company's internal network, IT admins need to assign IP addresses to hundreds of devices and configure subnets to ensure easy communications between networks. In such cases, a 4-octet format is used by the IPv4 IP address along with Class A, B, C, D, and E networks. IP stands for Internet Protocol, and V4 stands for Version 4 or IPv4. IPv4 addresses are 32-bit integers expressed in decimal notation. For example, 192.0.2.126 is an IPv4 address. It helps manage IP addresses across different environments, such as home networks or large corporations. Let's now discuss parts of IPv4. The first is the network part. It indicates the unique identifier assigned to the network. It also identifies the class of the assigned network. Next is the host part. This part uniquely identifies the individual machine on the network. This segment of the IPv4 address is assigned to each host. While the network part remains consistent across all hosts on the network, the host part must vary. Then is the subnet number. This is an optional part of IPv4. Large local networks with numerous hosts are divided into subnets, with subnet numbers assigned accordingly. Let's discuss the schema of the IPv4 addressing. IPv4 uses a 32-bit addressing schema divided into 4 octets of 8 bits each. Each octet represents 8 digits of base 2 binary, which can have values ranging from 0 to 255 in decimal notation. This is because 2 raised to the 8th power equals 256. Expressed in decimal format, IPv4 addresses range from 0.0.0.0 with all bits off to 255.255.255.255 with all bits on. Since the value of any of the 4 octets can range between 0 and 255, IPv4 provides a total of 4,294,967,296 possible addresses. Let us now understand how to convert an IP address to a binary. IP address to binary is a system interpretation of these addresses. Let's discuss how to convert each octet from decimal to binary through an example. For the decimal number 10, you can check the 16 placeholders. Since 16 is greater than 10, we place a 0 there. Moving to the next placeholder, 8, we subtract 8 from 10, which gives you 2 as a remainder. Thus, the 8th placeholder gets 1. The next placeholder, 4, is greater than 2, so it gets a 0. Since 2 is equal to 2, the 2 placeholders get 1, and you have 0 left over. Any remaining placeholders get a 0. Thus, Each octet contains 8 bits, explaining why it is called an octet. An IP address comprises the network and host portions. Let's discuss what they are. The network portion is common to all attached devices, which helps to identify the network, whereas the host portion is used to identify a particular device attached to the network. Network and host portions can be configured on your computer, but most modern systems use DHCP, Dynamic Host Configuration Protocol, to automatically configure IP addresses. Note that the size of the host portion determines the number of hosts or endpoints that the network segment can support. Initially, IPv4 networks used a classful addressing schema, which provided 5 distinct address ranges. Class A networks. They range from 0.0.0.0 to 127.255.255.255, used primarily for unicast communication. The default subnet mask for Class A is 255.0.0.0. In Class A networks, the first octet is used for the network portion, and the last 3 octets are for the host portion. Class B networks. They range from 128.0.0.0 to 191.255.255.255. The default subnet mask is 255.255.0.0. Class B networks use the first 2 octets for the network portion and the last 2 for the host portion. Class C networks. They range from 192.0.0.0 to 223.255.255.255. The default subnet mask is 255.255.255.0. In Class C networks, the first 3 octets are dedicated to the network portion, and the last octet is for the host portion. Class D networks. They range from 224.0.0.0 to 239.255.255.255 and are reserved for multicast groups. Protocols such as BIOS use addresses in this range to communicate. Class E networks. They range from 240.0.0.0 to 255.255.255.255 and are reserved for experimental and future use. With all the structure and characteristics of IPv4, it also comes with certain restrictions. Let's list them. IPv4 addresses help identify endpoints on a network with a unique IP address only. While dealing with multiple hosts, only use an IP address from a higher class. It comes as complex host and routing configurations, non-hierarchical addressing, and difficulty in renumbering addresses. It is also difficult to manage large routing tables, ensure security, provide quality service, multi-homing, and multicasting. To manage these limitations, IPv6 was introduced. In this video, you learn that IPv4, or Internet Protocol version 4, is the foundational protocol used for identifying and locating devices on networks since its introduction in 1983. It utilizes a 32-bit addressing scheme divided into 4 octets, each representing a segment of the address, crucial for network and host identification. Class A, B, C, D, and E networks categorize addresses based on their range and intended use, from unicast communication to multicasting and experimental purposes. Despite its widespread adoption, IPv4 faces challenges such as address exhaustion due to the rapid growth of Internet-connected devices, prompting the development of IPv6. Welcome to IT Protocol and Traffic Routing. After watching this video, you will be able to discuss the function of IP protocol and IP addresses, identify and explain routable protocols, subnet masks, and default gateways, explain the components of the IP header, utilize network masks, and identify broadcast IP addresses. Internet protocol and IP addresses are essential to route the data packets between devices within the network and across the Internet, ensuring reliable communication and connectivity. Let's explore the various aspects of the IP networking, including the IP protocol and IP addresses, and related concepts crucial for network administration. The Internet Protocol, or IP protocol, works with Layer 3 devices that use the IP header to identify and process network traffic that flows in the form of packets. All routers inspect the destination address of each packet, but stateful firewalls also inspect the source address to identify the source of the traffic. On the other hand, IP addresses are represented by a quad dot notation or a string of 4 numbers separated by dots. For example, 10.195.210.10. In this example, there are 4 octets or 4 groups of 8 binary bits separated by dots. In decimal form, an 8-digit binary number can take on a value from 0 through 255 and is always a positive integer. In binary form, the range is expressed as 00000000 to 11111111. An IP is a usable routable, which means it can be routed outside the network it originated in. Normally, this would be the Internet. However, note that not all IP addresses are routable. Routing is the path for data, which travels in the form of packets within or outside a network. These packets contain information and a header information at the beginning called IP header. Let's discuss what that is. An IP header has various components. The version of the protocol, whether it's IPv4 or IPv6, is the first thing declared in the header. The next crucial element is the TTL, meaning time to live. When a packet is sent, a TTL value is set to limit the number of hops the packet can take before it's disregarded. Each time the packet is inspected by a level 3 device, the TTL is decreased by 1. When it hits 0, the router drops the packet instead of forwarding it. This is done to prevent packets with bad IP addresses from bouncing all around the Internet forever, leading to unmanageable congestion. TTL is an 8-bit field, hence, it can contain values from 0 through 255. But the Internet Standards Committee recommends the TTL be set at 64 for most normal traffic. Note that TTL is measured in hops for the IP protocol, but in some protocols like DNS, it's measured in seconds. The next component is Protocol ID. Each protocol has an ID which acts as an identifier to determine the data layout. For example, ICMP or ping is Protocol 1, TCP is Protocol 6, and UDP has an ID of 17. Next is the source and destination IP address. The source IP address identifies the endpoint that is sending this packet, and obviously, the destination IP address is where the packet is being sent. The final important component is the payload. It is the content of the message that's being sent. All systems and networks are prone to downtime, and so, there is a need for a packet analyzer that helps to troubleshoot the issues. Wireshark is one of the most commonly used packet analyzers. Let's discuss it. Wireshark is used to capture packets, where the frame is seen first, followed by Layer 2 data and Layer 3 data. In this case, it is the IPv4. It is then followed by the source IP address and destination IP address. In addition to all these, IP addresses also have crucial components such as network masks, IP address prefixes, and default gateway. Let's explore them. Network mask, also called the subnet mask, is the assignment of bits to be used by the host or router to determine how the network and the subnet information are partitioned from the host information in the IP address. /24 at the end of the IP address indicates the first 24 bits or 3 octets of a particular IP address represent the network portion, while the remaining 8 bits or 1 octet are dedicated to the host address. The network mask is what accomplishes this division of an IP address into a network and a host segment. Let's now discuss the IP address prefix. The broadcast IP address is, in a sense, the opposite of a network mask. In this case, the broadcast IP address will have the octets for the network portion of the original IP address, with the octets or bits for the host portion turned on or all set to 1. Thus, all the bits of the host portion of the address are turned on. For this computer, the IP address is 192.168.52.3, and the broadcast address would therefore be 192.168.52.255. On this server, you will find an IP address with the prefix of 24. Here, 24 means the first 24 bits or 3 octets for the network portion, and the last octet is for the host portion. Let's now discuss default gateway. When a packet is created that must go outside of the local network to a specific address, it is sent to the default gateway. This is the router that acts as our default gateway to forward the packet outside of our network segment. The default gateway helps to manage the traffic going to points outside of the network or coming in from outside. In this video, you learn that Internet Protocol, IP, and IP addresses route data packets within networks and across the Internet for reliable communication. Routable protocols, like IP, can be routed outside the originating network. Understanding subnet masks and default gateways is crucial. The IP protocol header includes the version IPv4 or IPv6 and other elements necessary for packet inspection and processing. Source IP addresses identify the sender, and destination IP addresses indicate where the packet is being sent. Network masks divide an IP address into network and host segments. The prefix indicates the number of bits used for the network portion. Default gateways forward packets outside the local network, managing traffic between internal and external systems. Broadcast IP addresses have all host portion bits turned on, allowing communication to all devices in a network segment. Welcome to Introduction to IPv6 Address Schema. After watching this video, you will be able to discuss the structure of the IPv6 address, explore the concepts of unicast, multicast, and anycast in IPv6, describe the fields within an IPv6 header compared to IPv4, list the advantages of IPv6. As the world moves towards digitization, the need for a more robust and secure addressing system has become paramount to protect sensitive information and networks from any malicious attacks. One of the most prominent methods to deal with this is managing and monitoring IP, which continues to adapt to the growing needs of security requirements. While IPv4 is the most used protocol, IPv6 has evolved as the successor of IPv4, with more advanced capabilities that include increased address space, built-in security features, and improved efficiency. Let's compare the structure of IPv6 over IPv4. The IPv4 addresses were 32 bits long, whereas the IPv6 extended the address lengths from 32 bits to 128 bits. IPv4 address is 4 8-bit octets, and IPv6 deals with hex numbers. Finally, IPv4 faces a shortage of IP addresses, which is resolved with the help of the latest version of IPv6. Let's explore the IPv6 address in detail. An IPv6 address being 128 bits long is 4 times longer than the 32-bit IPv4 address, but that does not give us only 4 times as many addresses. Each IPv6 address is divided into 8 4-digit hexadecimal values, each separated by a colon. Each single hexadecimal digit can have 16 possible values, which makes it a 4-bit long binary. Hence, a group of 4 hex numbers would be 16 bits. And there are 8 of these in the IPv6 address, so 8 times 16 brings us up to 128 bits. IPv6 communicates to other devices via different addressing schemas. Let's discuss them. There are 3 different types of addressing schemas allowed in IPv4: unicast, broadcast, and multicast. The unicast mode is the most common IP addressing method, where one computer communicates with just one other system. That is, one-to-one data transmission from one network point to another. An address uniquely identifies a single node on the network. Unicast is supported in both IPv4 and IPv6. In broadcast mode, one computer communicates with all the other systems on that same subnet. Note that the network portion of the broadcast address is the same as the network portion of every other computer on that subnet. But the host portion has all the bits turned on or set to 1 to ensure that the packets are sent to all the endpoints on the subnet. Multicast is a one-to-many arrangement. A group of systems can be subscribed to a multicast address, so anything sent by that address will be received only by the systems that are subscribed to receive multicast from that system. The Class D addresses 224.0.0.0 to 239.255.255.255 define the multicast group. In IPv6, things are a little different. Unicast and multicast are essentially the same, but broadcast is replaced by anycast. An IPv6 anycast address is an address that's assigned to more than one interface. Typically, the address belongs to different endpoints. The IP header is required to support IP addressing schema as it contains the source and destination IP address necessary for routing packets. Let's explore the components of the IP header. Some of the most important components in an IPv4 header are the version, time to live, protocol, source IP address, and destination IP address. The IPv6 header, on the other hand, has fewer components compared to the IPv4 as shown. The first field, of course, is the version. Here is the source IP address, but instead of being 32 bits long, it's 128 bits long, as is the destination address. Let's now look at the rules to represent an IPv6 address. You don't need to specify leading zeros in the address. You can use a double colon to represent any number of consecutive zeros. For example, instead of writing 0:0:0:0:0:0:0:0:0:1, you can use a double colon 1. Also, there is one exception to this rule. You can only use the double colon replacement once in an IPv6 address. IPv6 addresses can be written in mixed notation with IPv4 for compatibility. For example, FFFF192.0.2.128 represents an IPv4 mapped IPv6 address. The longest sequence of consecutive zeros should be compressed. For example, 2001.001.0001 should be written as 2001.001.1. Now, let's list a few advantages of IPv6 address. IPv6 supports unique addresses, essential for growing Internet-connected devices. IPv6 includes a built-in IPsec for data integrity, authentication, and encryption, guarding against attacks. IPv6 also features a simpler, more efficient header structure, reducing processing costs and boosting speed. Compared to IPv4, IPv6 has better QoS features for prioritizing critical applications, ensuring necessary bandwidth and low latency. And IPv4 offers better support for mobile devices, enabling faster and more secure Internet connections. In this video, you learn that IPv6 extends IP addresses from 32 bits to 128 bits, vastly increasing the number of possible addresses. IPv6 addresses use 8 groups of 4 hexadecimal digits, separated by colons. In IPv6, a double colon can replace consecutive zeros in an address, but can only be used once. IPv6 headers are simpler and more efficient than IPv4 headers, improving processing speed. IPv6 supports unicast, multicast, and anycast, replacing IPv4's broadcast method with anycast. Welcome to Basics of Network Routing. After watching this video, you will be able to discuss the differences between Layer 2 and Layer 3 network addressing, describe the process of the address resolution protocol, explain the role of routes in routing tables. In organizations, a network administrator is tasked with ensuring that all office computers can access a shared network printer. In such scenarios, it would be the Layer 2 and Layer 3 network addressing, which assigns a static IP address to a printer, ensuring each computer in the office has a unique IP address. Let's delve into the details of the Layer 2 and Layer 3 network. Layer 2 addresses, known as MAC addresses, are embedded in network interface cards and act as physical identifiers, facilitating communication within broadcasting domains, such as segments of a network where devices use MAC addresses to communicate. In contrast, Layer 3 addresses, or IP addresses, are used for logical addressing and routing data packets across different networks, ensuring effective data transmission between these segments. Now, let's explore the Address Resolution Protocol, ARP, which bridges Layer 2 and Layer 3 addressing by mapping IP addresses to MAC addresses. The process of ARP makes sure that the data sent to an IP address reaches the correct device within a local network. The ARP process ensures that computers can resolve the printer's IP address to its MAC address using ARP, allowing them to do the printing job correctly. Now that it is clear that ARP ensures the data is sent to the correct device's IP address, It is also important that the traffic is directed from the office computers to the printer's IP address via the proper routes. This is done with the help of routers and routing tables. Routing tables, which you'll find in every network device, play a crucial role in determining the best path for data packets. These routing tables are distinguished into different types of routes. Let's delve further. The two types of routes are the default routes and the direct routes. In this video, you'll learn that Layer 2 addresses or MAC addresses are embedded in network interface cards and serve as physical identifiers. Layer 3 addresses or IP addresses are used for logical addressing across networks. The ARP process ensures that data sent to an IP address reaches the correct device within a local network, and routing tables help determine the best path for data packets. Welcome to Layer 2 and Layer 3 addressing. After watching this video, you will be able to discuss the function of IP protocol and IP addresses, define ways to find MAC addresses on various OS, explain Layer 2 and Layer 3 addressing. Systems and networks connect to a private or public network using network interfaces that are integrated within them. Network interfaces may be a single chip or a whole network interface card, commonly referred to as NIC. Your NIC could support a wired connection, a wireless connection, or both. It contains a burned-in physical address, also known as the complete or MAC address. Note that the MAC address is physically encoded on the NIC and cannot be changed. Attackers tend to trick operating systems or configure them into representing the MAC address of their interfaces using a different address. However, to do this, the attackers should know the MAC address of a system. This is known as MAC spoofing and can be used to bypass MAC address filtering that is set up on a firewall to protect assets by limiting access to only those machines that have been previously granted access. Usually, the MAC address is 48 bits long or a string of 48, ones and zeros, divided into 6 octets or 6 groups of 8 bits each. The first 3 octets are reserved to identify the manufacturer of the NIC and are called the Organizationally Unique Identifier, OUI. The last 3 octets are used by the manufacturer to identify each unique card. To see your computer's MAC address, open a terminal or command prompt window. On Linux systems, run the ifconfig command. Similarly, on Windows systems, run ipconfig/all, and the physical address is listed among the many other parameters in addresses. Let's discuss the step-by-step process of connecting to a router and discuss the details of network interfaces and MAC addresses. In this example, we'll use a secure shell or SSH to connect to the router. Enter the password to view the information for all the interfaces. Remember, each individual network interface has its own address, regardless of the number of network interfaces in a single device. Look closely at the Layer 2 MAC address. This is the physical address or MAC address of my system, and this is the broadcast address that can be used to send a message to all the devices in this network segment. Notice that the MAC address does not appear at 6 groups with 8 zeros in each group, but is condensed by representing each binary octet by 2 hexadecimal or base 16 numbers instead to make them easier for humans to work with. The computer still sees the 8 ones and zeros, but displays only hex numbers for our benefit. When the packet is sent from one computer to another, the packet header will contain both the Layer 2 and the Layer 3 address. The packet is delivered to the Layer 2 MAC address. Then, the computer verifies that Layer 3 for IP address and header matches its own IP address. The system ensures that the Layer 2 MAC address and the packet header matches the system to start sending the packet. Broadcast domains are the segment of the network when the computer is on. Looking at the router logged here, there are many network interfaces comprising of InPost 3, InPost 8, and InPost 9. So, this device is connected to 3 different networks, which means 3 different broadcast domains. Observe that the local IP address here is same as the broadcast address. If the packet is sent to the broadcast address, all the endpoints within that broadcast address will receive the packet. Broadcast domains can also be called virtual LANs or VLANs. In this video, you learn that network interfaces may be a single chip or a whole network interface card, commonly referred to as NIC. MAC spoofing is used to bypass MAC address filtering by setting up on a firewall to protect assets. MAC address is 48 bits long, or a string of 48, ones and zeros, divided into 6 octets, or 6 groups of 8 bits each. Broadcast domains can also be called virtual LANs or VLANs. Welcome to Routers and Routing Tables, Part 1. After watching this video, you will be able to discuss routing tables, describe routing interfaces. Communication across servers and networks is critical to internal communication within an organization, as it facilitates a seamless flow of data which is secure and free from any vulnerabilities. Within a network, this process is aided by routing tables, which play a very important role in directing and optimizing network traffic. Let's discuss what it is. Routing tables are essential components within a network, as they help direct data packets to their intended destinations. When discussing routing tables, it's commonly assumed they are only for routers. However, every device connected to a network, whether a computer endpoint or server, maintains its routing table. Let's discuss the key features of routing tables. Every entry in a routing table consists of network destinations and an interface to reach them. When a device receives data, it checks its routing table to determine the best path based on destination IP addresses. If the destination is on the local network, the data is sent directly, or else it's forwarded to a gateway, which routes it further. Routing tables dynamically update to adapt to network changes, ensuring efficient data transmission. Let's use a virtual machine configured as a router to demonstrate. To view the routing table, we use commands like netstat-nr on Mac OS X or Windows systems. Currently, the table shows routes for packet delivery. If an IP address isn't listed, packets are sent to the default gateway, which forwards them to the next hop. Within the network, specific interfaces like ENP0S9 handle traffic within their broadcast domains. Other interfaces, such as ENP0S8 and ENP0S3, are also connected, with one acting as an endpoint and another as the default gateway. Switches, which rely on MAC tables, handle packet delivery differently. They refer directly to the Layer 2 MAC address in a packet's header for delivery, without inspecting Layer 3 information. If a matching MAC address is found in the table, the packet is directed to the correct interface. In this video, you learn that routing tables are crucial in directing and optimizing network traffic within organizations, ensuring seamless communication across different departments and buildings. Specific network interfaces, e.g., ENP0S9, ENP0S8, ENP0S3, handle traffic within their respective broadcast domains, while switches use MAC tables for efficient packet delivery based on MAC addresses. Welcome to Address Resolution Protocol. After watching this video, you will be able to discuss Address Resolution Protocol, ARP, explain the ARP table, explore MAC addresses and routing. Understanding how data moves across networks is essential in today's interconnected world. Home, office, or data center networks rely on various protocols and tools to ensure smooth communication between devices. One of the fundamental protocols involved in this process is the Address Resolution Protocol, ARP. Every device connected to a network has an IP address. This unique identifier allows it to communicate with other devices. However, for the data to reach the correct device and the IP address, the device's physical address, known as the MAC address, is also needed. And that's where ARP comes into play. ARP resolves IP addresses to MAC addresses for accurate data routing. Let's discuss it. Address Resolution Protocol, ARP, troubleshoots network issues and sets up new devices. Understanding ARP involves recognizing that devices must find the MAC address corresponding to a given IP address. This mapping is stored in the ARP table, which helps devices locate these addresses efficiently. Let's examine the ARP table on the Linux router. The ARP table can be viewed on any Windows, Linux, or Mac OS X system by running the ARPA command in a terminal or command prompt window. The Linux router has its own set of commands for displaying information, so when the prompt IP neighbor show is run, it displays all the MAC address information on a particular device. The IP address 172.16.52.1 is connected to ENP0S8 and has the logical or MAC address shown here. Notice that ENP0S8 is within the broadcast domain or local network, and that 172.16.52.101 is the decider range. Let's take an example of an ARP table from a Windows machine. To begin with, on Windows machine, use the common ARPA in a command prompt window, which displays the ARP table. This data can also be seen in a Wireshark packet sniffer. The address resolution protocol and reply can be viewed if the packet is selected. Here are the IPv4 and source MAC addresses for this packet. These are the source IP address and the destination IP address. In this case, a router and the destination can be viewed with the same IP address and the MAC address as above. Let's discuss a practical scenario for implementing this. Suppose a ping is needed on a device within the network, but the translation from the IP address to the MAC address is not working. Then, a TCP dump is started on the interface ENP0S9 on another screen to capture traffic information. Pipe this to APCAP or packet capture file and leave it running. Now, check the ARP table and ping a device missing in the ARP table. It was noticed that 192.168.52.100 was pinged successfully. Stop the capture and see that the results are transferred to the desktop. Let's now understand the ARP operation. The first observation is that before a ping can be successful, the computer must obtain the physical address of the target IP address. This is because a packet is never delivered to an IP address, but always to the physical or MAC address. Now, when a computer attempts to ping an IP address, such as 192.168.52.100, it first tries to find its MAC address by querying all other computers on the local network. The source address is displayed here while the destination is broadcast. This frame is sent to all other devices in the broadcast domain. Any device with the address 198.162.52.100 informs if it exists on the network, effectively answering, "Who has this IP address?" The computer initiating the ping, 192.168.52.4, needs a response. By checking the router again, you can confirm that this is the computer's IP address. The second line shows the response from the computer with the MAC address, and the message is sent to the querying MAC address. The message indicates that 192.168.50.100 has this MAC address. The ping can be transmitted once you populate the ARP table with this translation. Thus, the Internet Control Message Protocol, ICMP, echo request, and the ICMP reply can be viewed here. Thus, the Address Resolution Protocol translates IP addresses into the MAC addresses needed for communication systems. Let's now discuss how MAC addresses broadcast domains and how routing helps network communication. It's essential to note that only the MAC address of the destination is needed to transmit data within the same broadcast domain. However, when sending packets to a different broadcast domain, the MAC address of the default gateway, typically the router, is needed. Therefore, let's examine the routing table. Here, the default gateway is identified by the address 10.0.4.2. Now, if you want to ping google.com, you do not need to find the MAC address of the default gateway, as 10.0.4.2 is already available here. In this video, you learn that Address Resolution Protocol, ARP, is pivotal in networking, translating IP addresses to MAC addresses for effective data transmission across devices within the same broadcast domain. The ARP table, accessible through commands like ARPA, provides crucial mappings of IP addresses to MAC addresses, aiding in troubleshooting the network management across different operating systems. MAC addresses are essential for transmitting data within the same broadcast domain or local network. Welcome to Routers and Routing Tables Part 2. After watching this video, you will be able to Discuss the key components of network communication. Explain how packets travel through various routers and networks. In organizations, there is always a need to share confidential information within networks and systems. Effective and safe communication across networks is critical for overall organizational success. Let's discuss a few important key components required in network communication. Network communications happen with the help of the broadcast domain, or the network segment where all the devices communicate directly with each other at the data link layer. Additionally, there is a default gateway and a router that connects a local network to other networks. Network communication also uses a routing table, a data table stored in a router or a networked computer that lists the routes to network destinations to determine the best path to forward packets to their destinations. Last but not least, the routers use an APR table to match IP addresses with MAC addresses for devices on the same network. Let's discuss how routers facilitate network communication. The data packet travels through various routers using default gateways and ARP tables to ensure it reaches the correct destination. The process involves different networks connected via different routers to send a packet. Let's understand the connections. This broadcast domain is called the Network 1, which is connected to a Layer 3 device, which in this case is a router, but it can be a firewall or a switch too. Now, this router is also connected to Network 2, which is also the broadcast domain 2. Now, Network 2 is connected by a second router to Network 3, which is the third broadcast domain. Once the connections are established, the process of sending a packet begins. If a computer in Network 1 wants to send a packet to a device in Network 3, it only needs to have a default route configured pointing to its default gateway. In this figure, it is port 1 of the first router. For example, this router checks if device 1.8 wants to send a packet to device 3.6 in Network 3. If the first router is not directly attached to device 3.6, it will send the packet to its default gateway, which in this case is port 1 of the second router. The second router identifies that device 3.6 is directly connected to its port 2 and will deliver the packet to device 3.6. It must have its ARP table populated with device 3.6's MAC address. Let's call this MAC address AD. For device 3.6 to respond, the second router must know the path back to device 1.8 via the first router. Both the forward path and the return path must exist for device 1.8 GB to receive a reply when pinging device 3.6. Thus, the packet is sent successfully. In this video, you learn that networks are interconnected through routers spanning multiple broadcast domains. Packet delivery across networks is facilitated by configuring default routes and maintaining ARP tables. Routing tables within routers are crucial for determining the most efficient paths for packet forwarding. ARP tables play a key role in routers by mapping IP addresses to MAC addresses for devices on the same network. Routers enhance communication between departments by facilitating reliable document transfer across distinct network segments. Welcome to Routes and Routing Tables, Part 3. After watching this video, you will be able to discuss the different types of routes in a routing table, explain how networks send packets via routing tables. Computers and servers are connected through a network, sharing their data across various systems. This data that moves from one computer to another relies on routing tables, MAC addresses, and ARP tables. Let's break down the components and understand them, starting with routes. Routes are of 3 types: default route, connected route, and dynamic and static routes. Let's discuss them. The default route is used to send data to destinations not specifically listed in the routing table, making it the default route used to send packets to addresses for which no other information is available. For example, in a scenario where you must send a packet to IP address 4.2.2.2, but you know nothing about this network, the packet will be sent to the default gateway, for which the default gateway for this subnet is 10.0.4.2. The packet is sent there, and the default gateway will take care of routing it to another network. Note that a successful reply is generated for the ping. Let's discuss the directly connected route. These routes indicate a network directly connected to a router's interface. For example, there are 3 more routes shown here, which are directly connected to our server, Hence, this network exists connected to this interface, and the same for these other two. Next are the dynamic and static routes. A network administrator manually sets static routes. The dynamic routes are automatically updated through different dynamic routing protocols, such as the OSPF, RIP version 1, RIP version 2, and EIGRP, a Cisco proprietary protocol. Looking again at our example of sending data from network 1 to network 3. This is a small network and it can contain only router and server 100 and server 200. Let's use the SSH to log in as root to server 100 at IP address 192.168.52.100. Now, let's say you want to ping to server 200 from server 100, where the service is not known, which means you don't have the DNS translation enabled. The IP address of server 200, which is 172.16.52.100. So, let's ping that, and you will notice that the ping is successful. Now, let's check the routing table to see how the router ensures that this packet is delivered to server 200. Here, you can view the router action. Note that there isn't a route that points directly to 172.16.0.0. Hence, you are trying to ping. But here, our default gateway is connected to the interface ENP0S3. So, the packets are being sent to the default gateway, and the default gateway ensures that this packet is delivered. The default gateway also ensures that the reply is routed back to you. You can run a trace to see exactly how this packet is routed from the local host through the gateway. The gateway ensures that the packet is delivered to its destination endpoint. You can see here that 172.16.52.0 is not directly connected to the interface. In this case, you only have one interface. You have the loopback, which is a logical interface, and we have ENP0S3, which is the physical interface for this device. There are two IP addresses assigned to the same interface, which is perfectly valid. Here's our MAC address. If you check the ARP table, you'll see that the ARP table is only populated with devices that are directly connected to our interfaces, meaning from the same broadcast domain. In this case, the only interface you have within this network segment is 192.168.52.324. So, the ARP table is populated with only that address. Even though you're pinging 172.16.52.100 and the ping is successful, the 172 addresses will not be added to this ARP table. Again, the ARP table will only translate addresses within our local broadcast domain. When sending data to a remote IP address, you should know the MAC address of our default gateway. In this case, when you check the routing table, the default gateway IP address is 192.168.52.4. You can look up that address translation in the ARP table. The entry for this IP address is the physical address. 08:00:27:84:64:A5. It should be obvious by this point that each IP address will have a different MAC address because the MAC address is the physical or burned-in address for that interface. So, that's how you can send packets across the different network segments. The default gateway ensures that the packets are delivered to the closest Layer 3 device until it finds a Layer 3 device that has the destination system directly connected to one of the interfaces. In this video, you learned that default routes serve to forward packets to destinations not explicitly listed in the routing table, ensuring connectivity even when specific network details are unknown. Directly connected routes indicate networks accessible through a router's interfaces, simplifying communication within immediate network segments. Dynamic routes, managed through protocols like OSPF and EIGRP, automate route updates based on network conditions, enhancing efficiency and adaptability in complex network environments. Networks determine packet forwarding paths using routing tables, directing traffic based on destination IP addresses. Welcome to Application and Transport Protocols, Part 1. After watching this video, you'll be able to differentiate between TCP and UDP based on their characteristics, explain the structure and purpose of TCP and UDP packet headers, including the significance of source and destination ports, and identify real-world applications of UDP and explain why UDP is chosen for those applications over TCP. Let's begin by differentiating between Transport Control Protocol, or TCP, and User Datagram Protocol, or UDP, based on their characteristics and use cases. Transport Control Protocols, or TCP, are like the envelope you put a letter into. TCP is similar to an envelope where you write the sender's address, the destination address, and other information. Like the front face of the envelope, the packet header identifies the sender, the intended recipient, and other information. TCP is similar to sending an envelope with a tracking number and the receiver's signature to ensure the letter reaches its intended recipient. TCP sets up a connection and provides an ordered list of packets sent and received for both the sending and receiving computers. But all that handshaking requires a time-consuming overhead. Many applications require that they receive their data packets in the correct order and that lost packets be resent. In contrast, UDP sends the data to its destination without a delivery confirmation. Like sending bulk mail, using UDP is fast and inexpensive. With UDP, most or all of the information will reach its intended destination, but the sender never receives a delivery confirmation. UDP transfers data differently from TCP. The UDP omits confirmation of packet receipt to the sender, and the receiver can only reassemble the data stream in the order the packets arrive, even if some are not in the order they were sent. UDP requires little overhead, so it's a high-speed protocol. UDP is suitable for streaming videos and music, where the loss or order of a few packets is insignificant. So, which protocols do applications prefer? Each application has its preferred protocol. Some applications prefer UDP, and other applications prefer TCP. Next, learn about common UDP protocols and their real-life uses. UDP protocols specify source and destination ports to direct data packets to the correct application, ensuring proper communication between devices on a network. Common UDP protocols are TFTP and the Trivial File Transfer Protocol on port 69. This protocol is very similar to FTP, but uses UDP instead of TCP to avoid the overhead of establishing and maintaining a connection to transfer very small files. DNS, the domain name system, uses port 53. It uses UDP for its name queries. However, DNS might use TCP for less common tasks. DNS commonly translates domain names into IP addresses. SNMP, the Simple Network Management Protocol, uses ports 161 and 162. It is uncommon, but SNMP can also use TCP. SNMP translates domain names to IP addresses to monitor and manage network devices. DHCP, the Dynamic Host Configuration Protocol, uses port 67. DHCP automatically assigns and manages a pool of IP addresses to the systems that are subscribed to it. VoIP, or Voice over IP, uses port 5060. VoIP can also use TCP, which is used to send voice over the Internet. IPTV, or Internet Protocol Television, streams TV signals. IPTV uses both UDP and TCP and ports 80, 5004, and 12,000, depending upon which service is in use and whether the traffic is inbound or outbound. These protocols take advantage of UDP because its transmission speed and dropped packets do not affect overall data outcomes. In this video, you learn that TCP packet information contains the sender, an identifying recipient, data verification packets, and a list of packets in order. TCP data transmissions include information that enables the receiving computer to verify receipt of all the packets and their order. UDP sends data packets without confirming that the correct computer received the data packets. UDP might send the packet data out of order and not verify that the receiving computer received all the packets. UDP protocols specify source and destination ports to direct data packets to the correct application on a device for proper communications. And FTP, DNS, SNMP, DHCP, VoIP, and IPTV use UDP and specific ports for fast, efficient data transfer, often prioritizing speed over reliability for file transfers, name queries, IP management, voice communication, and TV streaming. Welcome to Application and Transport Protocols UDP and TCP Part 2. After watching this video, you will be able to discuss the mechanism of TCP, outline the steps of the TCP three-way handshake, describe the components of the TCP header, and list the applications that use TCP. Network communications can be direct or real-time. Organizations use TCP or Transmission Control Protocol and User Datagram Protocol for UDP based on their requirements. TCP is a connection-oriented protocol that ensures reliable and ordered data delivery between applications. Meanwhile, UDP is a connectionless protocol that allows data packets to be sent without establishing a connection. TCP and UDP ensure that data packets are delivered successfully through secured connections. Let's discuss their working mechanisms. TCP connections start with a three-way handshake. First, the sender sends the recipient an SYN synchronize request to establish the connection. Then, the recipient responds with a SYN-ACK synchronize acknowledgement signal. Finally, the sender sends an ACK acknowledgement, establishing the connection. This process ensures that both parties are ready to communicate and agree on the initial sequence number for the data transmission. Let's understand this process with the help of an example. In this scenario, let's say that while trying to establish an SSH or secure shell connection from the system at 192.168.52.1 to the server at 192.168.52.100, you observe that these are the first three packets to be sent. This is the SYN and the flags over here. Each flag can take on only two possible values, 0 or 1. So, in this case, the flag is on. The next packet will contain the SYN-ACK. Here, the SYN is on and the ACK is on. The last packet only contains a simple ACK. Once the three-way handshake is successful, you can establish a TCP co and transmit data. To send packets continuously, the TCP segment must be acknowledged by the destination. Let's understand this process. In reality, TCP often sends data in series instead of waiting for an acknowledgement for every packet. The receiving computer can look at the sequence number to tell if a packet is missing from a series and lets the sender know to resend the missing packet. TCP also uses sequence numbers and acknowledgement numbers. Once a packet is received, the receiving system sends an ACK or acknowledge number. That ACK number is the sequence number for the next datagram segment, thus completing the process. Let's discuss the components of TCP. A TCP Transmission Control Protocol header is a crucial part of the TCP segment structure, ensuring reliable network communication. The header contains essential control information and fields that help manage data transmission. Let's break down the components of a TCP header. The example shows the packet capture, along with features like the source port, the destination port, the SYN, ACK flags, and several others. Let's look at an example to understand the functioning. Here's the Transmission Control Protocol on Layer 4. Note that for this packet, the source port is 58,038, and the destination port is 22. SSH uses port 22. This packet header shows that a process using local port 58,038 attempts to connect to a remote SSH server. The packet header contains the sequence number and an acknowledgement number. Now that you know the concept of TCP, let's list its applications. TCP is used in HTTP, the Hypertext Transport Protocol that connects the World Wide Web used for browsing the web. HTTPS, secure version of HTTP, encrypting data using SSL certificates. SMTP, simple mail transport protocol for sending emails. And FTP, file transfer protocol for transferring files. TCP is used very frequently in the HTTP request response cycle. Let's discuss it. HTTP works on a request response cycle. First, the client requests a web page, and then the server returns that page as a response, completing the cycle. The HTTP packet comprises 3 blocks: the start line, the header, and the body. However, as a cybersecurity analyst, knowing that HTTP protocol is not secure is essential. HTTPS, or Secure HTTP, was developed to address the need for privacy and security on the Internet. HTTPS incorporates SSL certificates to encrypt data and travel securely across the network. To be more precise, SSL acts as the outermost protocol layer, which means nothing after the initial handshake is exposed or sent unencrypted. In this video, you'll learn that TCP, Transmission Control Protocol, ensures reliable data transmission by establishing a connection, tracking data packets, and requiring acknowledgements. UDP, User Datagram Protocol, offers faster data transmission without establishing a connection or requiring acknowledgements. A 3-way handshake includes the sender sending an SYN request, the recipient responding with a SYN-ACK, and the sender replies with an ACK. The components of TCP include source and destination ports, sequence and acknowledgement numbers, and flags. And applications using TCP include HTTP, HTTPS, SMTP, and FTP. Welcome to the Domain Name System, DNS, and Dynamic Host Configuration Protocol, DHCP. After watching this video, you will be able to explain DNS and its services, discuss DHCP and its services. In organizations, employees use their devices to connect to the company network and browse any website address. Whether internal or external sites, they need a certain network service that helps in translation and assigning IP addresses for secure data transmission. That's where DNS and DHCP come into play. DNS, or Domain Name System, is a network service that helps translate domain names to IP addresses, and DHCP, or Dynamic Host Configuration Protocol, automatically assigns IP addresses to each device so that they can connect to the network without manual configurations. Let's understand the service provided by DNS. The first service is DNS resolution, where the DNS running on the local machine translates the domain names and URLs to IP addresses. That is, whenever you go to google.com, DNS will resolve that name to the actual address of Google's web server. So, whenever a domain is queried, such as by pinging google.com, the DNS service resolves the actual IP address of this server to use in the ping request. Thus, you should locate where the DNS server is hosted. In this case, the default gateway is 192.168.0.1, which handles the translation process. Note that the DNS service relies on devices with valid IP addresses assigned by the Dynamic Host Configuration Protocol, DHCP. Let's discuss it in detail. DHCP, or the Dynamic Host Configuration Protocol, allows a computer to automatically obtain an IP address whenever it connects to its local network from a pool of available IP addresses that the DHCP server has been configured to manage. The DHCP handshake consists of 4 packets that go between the requesting system and the DHCP server. They are known as Discover, Offer, Request, and Acknowledgement messages. Next, let's understand how the DHCP server works. When an endpoint connects to a network, if it's configured for DHCP, the system will immediately try to discover the DHCP server. So, it sends a broadcast message to all the endpoints on the network segment. If the endpoint has an IP address from a previous boot up, it may ask in the request to be allowed to renew a lease on that address, rather than be issued a new address. If there is a DHCP server on the network segment, there are endpoints configured for DHCP, and the DHCP server will send an offer message back to the requesting endpoint. The offer message has the MAC address of the requesting endpoint. the IP address that's being offered, the subnet mask, the lease duration, and the IP address of the DHCP server that's making the offer. A network may be configured with more than one DHCP server so that the requesting endpoint might receive multiple offers. After receiving offers, the endpoint will reply with a request message that indicates which offer is accepted. The winning DHCP server sends a final ACK or acknowledgement message to the endpoint, confirming that it can have the offered IP address, and then it marks that IP address as leased to the MAC address of the endpoint. The other DHCP service will return their offered addresses to their pools of available addresses. Let's discuss the DHCP service that DHCP uses Wireshark Capture. Wireshark captures packets sent to or from the system and displays them in human-readable format. It helps display the DHCP communication between the clients and the servers to diagnose any issues. This is a Wireshark capture of a DHCP Discover packet. Initially, the computer doesn't know the IP address or the MAC address of the DHCP server. Hence, you can note in Layer 2 that the requesting computer is using the broadcast MAC address, whereas in Layer 3, the broadcast IP address is used. And at Layer 4, you can use the boot PC, which is DHCP that uses UDP, runs on source port 68 and destination port 67. The DHCP server listens on port 67. Once it receives a DHCP request, it checks its pool of IP addresses to see if one is available. If it is one to lease, it will reply to the requesting endpoint with a DHCP offer containing the proposed IP address and related information, like the DHCP server's address, the address of the default gateway, the subnet mask, and the lease duration. Even though the endpoint now knows the address of the DHCP server, it will reply to the offer it has accepted with a request message that is broadcast rather than sent directly. This is to let any other responding DHCP servers know that an offer has been accepted and they can return their offered IP addresses to their address pools. For this part, here is the DHCP request packet. If you notice, it repeats the same IP data that was sent to the endpoint in the offer message. Finally, the DHCP server sends the acknowledgement message to the endpoint, confirming that it is leased at the previously sent IP address. In this video, you learn that DNS, or Domain Name System, is a network service that helps translate domain names to IP addresses. DHCP automatically assigns IP addresses to devices, eliminating the need for manual configurations. The DHCP process involves 4 main messages: discover, offer, request, and acknowledgement. Wireshark captures DHCP packets and helps diagnose issues in the DHCP communication process. Welcome to DNS filtering. After watching this video, you will be able to describe the concept of DNS filtering and its role in cybersecurity. Explain how DNS filtering operates to block access to specific websites or services. Identify the importance of DNS filtering in preventing cyber threats and enhancing network security. Explain the benefits of DNS filtering. And discuss the implementation of DNS filtering in different scenarios, considering factors such as security, compliance, and productivity. A domain name system, or DNS, evaluates human-readable domain names and determines which IP addresses, such as 192.0.2.1, the computer can use to locate the address within a closed network or on the Internet. DNS servers convert human-readable domain names into IP addresses. When you type a URL into your browser, your computer contacts a DNS server to find the website's IP address. DNS filtering uses the DNS system to block access to specific websites or services based on predefined criteria, including blocking sites known to distribute malware, restricting access to inappropriate content, or enforcing company policies. So when a user attempts to visit a website, the DNS filtering system checks the requested domain against a list of blocked domains and sends a request. The request is denied or redirected if the domain is on the blocked domains list, preventing access to harmful or unwanted content. Cybersecurity uses DNS filtering to prevent threats, control content, and enhance privacy. DNS filtering to block malicious sites is a frontline defense against cyber threats. By blocking access to domains associated with malware, phishing, and other malicious activities, DNS filtering helps prevent infections and data breaches before they occur. DNS filtering reduces attackers' potential entry points by limiting access to known bad domains, making it harder for them to compromise the network. Organizations can use DNS filtering to enforce internet usage policies, such as preventing employees from accessing social media during work hours or blocking access to adult content to comply with regulatory requirements. DNS filtering can help maintain employee productivity by blocking distracting or non-work-related sites. DNS filtering enhances user privacy and prevents attacks by blocking domains that serve ads, track user behavior, and inject malware. Next, learn how DNS filtering works. First, when a user enters a URL into their browser, the DNS system resolves the domain name to an IP address. The DNS filtering system intercepts the DNS query, which can happen using a DNS server configured with filtering rules. Next, the DNS system performs a policy check. The DNS filtering system checks the requested domain against its filtering policies, which likely include blocked and allowed sites. Then, based on the policy check, the DNS filtering system either allows the query to proceed, returning the correct IP address, or blocks the query, returning a predefined block page or an error message. Security-based filtering focuses on threats targeting domains known for hosting malware, phishing sites, command and control servers, and other cyber threats. Security-based DNS filtering prevents malware infections and data breaches by blocking these domains. Content-based filtering categorizes domains based on their content, such as social media, gambling, news, and others. Organizations can block or allow access based on these categories to enforce acceptable use policies and comply with regulatory requirements. Custom filtering allows organizations to implement tailored policies, creating their own allowed and disallowed lists to meet specific organizational needs. For example, a company might block access to computer websites or ensure access to specific business-critical sites. DNS filtering improves security, network performance, and compliance. By blocking access to known malicious sites, DNS filtering is a proactive defense mechanism, stopping threats before they reach the user's device. With fewer opportunities for malware to infiltrate the network, organizations experience fewer security incidents and breaches. DNS filtering reduces bandwidth use by blocking non-essential or harmful traffic. With fewer requests to malicious or unwanted sites, legitimate network traffic can flow more smoothly, improving user access to company resources. DNS filtering supports regulatory compliance by preventing access to inappropriate content and ensuring safe internet use. Many DNS filtering solutions provide logging and reporting features, offering an audit trail for compliance verification. You'll first evaluate and select a DNS filtering solution to implement DNS filtering. When selecting a DNS filtering solution, consider ease of use, customization options, reporting capabilities, and cost. After you purchase your DNS filtering solution, you'll deploy your system, ideally using both network and client-level filtering. Network-level filtering uses firewalls, dedicated DNS filtering appliances, or cloud-based DNS filtering services. It applies policies across all network devices. You can implement client-level filtering by installing DNS filtering software agents on individual devices. These agents apply filtering policies regardless of the network they connect to. Next, you'll need to configure your DNS filtering settings. Start with policy definition, where you define filtering policies based on your organization's needs. Configuration tasks might include blocking specific site categories, creating custom block and deny lists, or setting time-based access controls. You can apply different policies to different user groups, allowing for tailored filtering based on user roles and requirements. To maintain your system, review filtering logs and reports regularly to ensure the DNS filtering system is working effectively. Adjust policies as needed to respond to emerging threats or changing organizational requirements. Let's look at a case study example. In this scenario, a company wants to prevent employees from accessing social media sites during work hours to improve productivity and ensure that no one accidentally downloads malware from these platforms. The solution involves implementing DNS filtering to block access to social media sites and setting up alerts to monitor attempts to access these blocked sites. As a result, productivity improves as employees focus on work-related tasks, and the company experiences fewer security incidents due to social media-borne threats. In this video, you'll learn that DNS filtering supports cybersecurity efforts by using the DNS system to block access to specific websites or services, including malware. DNS filtering systems check the requested domain against a list of blocked domains and deny or redirect the request if required. DNS filtering blocks access to malicious sites, preventing cyber threats, infections, and data breaches, and reduces attackers' potential entry points. DNS filtering supports cybersecurity, controls the content, and enhances data privacy. And to implement a DNS filtering system, evaluate and select a solution, then deploy, configure, and maintain your system. Welcome to Syslog Message Logging Protocol. After watching this video, you will be able to describe the syslog protocol, explain the functions of a syslog, describe the 3 syslog layers, including content, application, and transport, identify the key players, discuss syslog message components. Let's first learn about the syslog protocol and its functions. Syslog is a standard abbreviation for message logging. The syslog protocol separates the software that generates messages, the system that stores them, and the software that reports and analyzes those messages. Syslog provides a message format that enables vendor-specific extensions to exist in a structured format. Each message is labeled with a facility code that indicates the software type generating the message, and then a severity label is assigned. System administrators use syslogs for system management, security auditing, general informational analysis, debugging messages, event notification messages, and forensic research. Syslog is vital for managing logs in a networked environment. It operates across 3 main layers: content, application, and transportation. Let's explore these layers. First, you see the content layer where the syslog stores the messages. Next is the application layer, which handles message generation, interpretation, routing, and storage. Finally, the transport layer manages the transportation of syslog messages across the network. Now that you know about the layers, learn about the players. Syslog has 5 key players. The originator is where the event occurs, like your local machine. The collector is the syslog server collecting the messages. The relay server forwards messages from the originator to the collector. The transport sender prepares messages for transport. And the transport receiver receives and delivers messages to the syslog server. Next, check out the syslog message process. The message process starts with the originator, creating and including the facility code and severity level. The syslog client adds an originator process ID, a timestamp, and the device's hostname or Internet Protocol address, IP address, to the information header before forwarding it to the server. The facility code values indicate which machine process created the message. The syslog protocol was initially written on BSD Unix, so facility code names reflect the names of Unix processes and daemons. If you receive messages from a Unix system, consider using the user facility as your first choice. Unix does not use local 0 through local 7, which is traditionally used by networking equipment. Cisco routers, for example, use local 6 or local 7. The syslog severity level ranges from 0, emergency, to 7, debug. Setting the severity level to identify significant messages, such as level 3, can ensure that only the network devices send and receive significant messages only, preventing your server from being overwhelmed. Here's an example of a packet capture of a syslog message. You can see the originator value, the collector value, the facility code, the severity level, and the actual message content. Next, let's recap what you've learned. In this video, you learn that the syslog protocol separates the software that generates messages, the system that stores them, and the software that reports and analyzes those messages. System administrators use syslog for system management, security auditing, general informational analysis, debugging messages, event notification messages, and forensic research. The syslog includes a content layer for storing messages, an application layer for message generation, interpretation, routing, and storage, and a transport layer for managing the transportation of syslog messages across the network. Syslog players include the originator, the collector, the relay server, the transport sender, and the transport receiver. Syslog message components include the facility code, severity level, the originator process ID, timestamp, and the reporting device hostname or IP address. Welcome to Flows and Network Analysis. After watching this video, you will be able to explain what a network flow does, identify the devices that provide flow data, and list the data available when viewing network flows. Network flows provide data and statistics on packets flowing through traversing interfaces. So, what devices provide network flow data? NetFlows collect samples of the flow's traversing interfaces using devices such as routers and switches. Next, explore the data provided using a network flow analysis tool. When inspecting a sample NetFlow record, the sample record reports how many packets have been used in this flow, how many bytes were sent, a timestamp recording of when the flow started, ports used where the sample was taken, including the identity of the incoming interface and the identity of the outgoing interface. These flows also provide quality of service and QoS information, including service type, and see what protocols are used. For example, ICMP is Protocol 1, UDP is 17, and TCP is 6. You will also see the source and destination IP addresses and all the source and destination port numbers for TDP and UDP. These charts, taken from a NetFlow server, show the source and destination IP addresses and all the source and destination port numbers for TCP and UDP. After NetFlow collects data, you can easily see which protocols are used most by this interface. In this case, more than 84% of the traffic is TCP, or World Wide Web traffic. NetFlow collects and displays this data for one interface at a time. You can also easily see the traffic categorized based on the application using the interface. It's no surprise that HTTP is number one. You can quickly determine how many bytes of data are ingressing or coming into the interface, and how many bytes of data are egressing or leaving the interface. You can quickly determine the number of packets being sent across the interface in each direction. Let's recap. In this video, you learned that network flows provide statistics about packet flow through routers. Network flows collect samples of the flows using devices, such as routers and switches. Network flow applications report on packet usage, bytes sent, time of day / timestamps, port utilization, QoS, application, routing and pairing, and protocols in use. And the NetFlow dashboard categorizes traffic based on the application that's using the interface, providing bytes of data and packet information. Welcome to this video about port mirroring and promiscuous mode. After watching this video, you will be able to define port mirroring and its significance, explain how intrusion detection systems help in port mirroring. With the rise in cyber attacks, network engineers and administrators need to constantly analyze and debug data to detect errors within the network. To do this effectively, they use a technique called port mirroring, which helps administrators monitor network performance and generate alerts when problems occur. Let's discuss this in detail. Port mirroring is when a switch is configured to make a copy of all the traffic traversing to one or more ports on that switch, and send the copied packets out to a single destination port. Port mirroring on a Cisco switch is generally called Switch Port Analyzer, or SPAN. There's also a Remote Switch Port Analyzer, or RSPAN, which allows the destination port to be remote or on a switch other than the one doing the collecting. Different vendors use different names for port mirroring. 3Com, for example, calls it RAP for Roving Analyst Port. However, if not used wisely, it can also be dangerous. Imagine the trouble that might result if an attacker could access a major switch within an organization and set up port mirroring to send a copy of all network traffic back to their servers for exploitation without detection. To fix this, you can send the mirrored packets to an IDS or an intrusion detection system connected to the destination port for analysis. IDS helps to monitor all the traffic in real time and send an alert if any anomalies are detected. Remember that an IDS is off to the side and only works on a copy of the network data. This means that the IDS will not slow down the network, but it also means that it cannot act directly on what it's found, like blocking the delivery of a packet. But it can only send out an alert to raise the alarm about what it's found. The endpoint or server being fed the mirrored data must have an NIC or network interface card running promiscuously to read all the frames it receives. Remember that these frames all have destination MAC addresses pointing to other systems. So, a NIC not in promiscuous mode would simply ignore them. To reiterate, for an IDS or other network analysis tool to work, it must have an NIC configured in promiscuous mode to read all the frames sent to its incoming port. A port sniffer, like Wireshark, helps put your NIC in promiscuous mode to capture all the traffic across its interface. In this video, you'll learn that port mirroring helps to analyze data and detect network errors. Remote Switch Port Analyzer, or RSPAN, allows the destination port to be remote. Intrusion detection systems, IDS, help to analyze destination ports and monitor real-time traffic to detect anomalies. Wireshark helps to put NIC in promiscuous mode. Welcome to User Behavior Analysis. After watching this video, you will be able to describe user behavior analysis, also referred to as UBA, explain user behavior analysis concepts, describe UBA techniques and tools, identify methods of implementing UBA, describe UBA implementation challenges, list roles and industries using UBA. User behavior analysis, or UBA, involves the systematic monitoring and detailed analysis of user actions within a network. Its primary purpose is to identify patterns and anomalies that could signal potential security threats. Unlike traditional security measures focusing primarily on external threats, UBA delves into internal user activities, helping to detect insider threats, compromised accounts, and abnormal behaviors that might go unnoticed. Traditional security measures often emphasize preventing external attacks. However, UBA provides an additional layer of security by focusing on internal activities. For example, suppose an employee who typically accesses specific files during regular business hours begins downloading large amounts of sensitive data late at night. In that case, UBA can flag these actions as suspicious behavior, warranting further investigation. This proactive approach helps detect suspicious behavior early and mitigate threats proactively. Now, explore user behavior analysis concepts, including baselining normal behavior, anomaly detection, and contextual awareness. Baselining normal behavior involves monitoring users to establish what constitutes normal behavior. This includes typical login times, access to specific files, and other routine activities. For instance, if an employee habitually logs in between 8 a.m. and 9 a.m. and accesses the sales database twice daily, this pattern is recorded as their baseline. Significant deviations from this pattern, such as accessing the database at unusual hours, are flagged for review. Anomaly detection identifies deviations from the established baseline. These deviations can signal potential security threats or policy violations. For example, if a user who seldom accesses financial records starts downloading numerous files, the system detects this as an anomaly and triggers an alert. Contextual awareness involves analyzing the context of user actions, such as their role, typical activity patterns, and current security policies. For instance, a high-ranking executive accessing sensitive files from an unfamiliar IP address during a vacation could be suspicious. In contrast, the system recognizes that it's normal for a high-ranking executive to access sensitive files from the corporate office during regular hours. Next, learn about some techniques and tools used in user behavior analysis, including machine learning algorithms, statistical analysis, and log analysis. Machine learning algorithms automatically learn and update user behavior patterns, enhancing anomaly detection accuracy over time. These algorithms are adept at recognizing subtle patterns and predicting potential threats based on historical data. For instance, a machine learning system might identify that employees who suddenly increase their access to confidential files are likely involved in data exfiltration attempts, prompting closer scrutiny of such behavior. Statistical analysis techniques quantify deviations from normal behavior. Some techniques, such as standard deviation, correlation analysis, and regression models, help assess the significance of observed anomalies. For example, if an employee's file access rate is 3 standard deviations above the mean for their department, this could trigger an alert for potential data theft. Log analysis involves scrutinizing logs from various sources, including access logs, application logs, and network logs, to provide a comprehensive view of user activities. Log analysis tools aggregate and correlate data to identify patterns and anomalies. For example, log analysis might reveal that an employee's login attempts originate from multiple geographic locations within a short period, suggesting possible credential theft and unauthorized access. Next, explore common user behavior analysis use cases, including detecting insider threats, compromised accounts, and data exfiltration. User behavior analysis helps identify malicious activities by insiders, such as employees or contractors, by detecting behaviors that deviate from everyday activities. For example, an employee who typically accesses customer data but suddenly downloads large volumes of intellectual property files could be flagged as an insider threat. UBA can effectively spot signs of account compromise by monitoring for unusual login patterns or access behaviors. For instance, if a user's account is accessed from a foreign country that the user has never visited, UBA can flag this as a potentially compromised account. Monitoring for unauthorized data transfers out of the organization is another crucial use of UBA. Monitoring identifies unusual data transfer patterns that could indicate data exfiltration attempts. For example, detecting large volumes of data sent to an external IP address through network flow analysis could suggest an attempt to exfiltrate data, triggering an investigation to prevent data loss. Next, explore UBA implementation methods. Effective user behavior analysis requires comprehensive data collection from sources, including network traffic, system logs, user activity records, and application logs. This data is crucial for establishing baselines and detecting anomalies. For example, collecting detailed logs of user access to databases, file systems, and applications provides a rich data set for analyzing user behavior. Integrating user behavior analysis with security information and event management (SIEM) systems enhances threat detection and response capabilities. SIEM systems aggregate and analyze data from various sources, providing a centralized view of security events. For instance, an SIEM system can correlate UBA data with system log messages and network flow analysis to offer a holistic security perspective. Continuous monitoring involves ongoing analysis to effectively adapt to changing user behaviors and emerging threats. For instance, regularly updating the UBA system to reflect changes in user roles, new hires, and evolving threat landscapes helps maintain its accuracy and relevance. Implementing privacy-aware practices is crucial for compliance with data protection regulations. For example, ensuring UBA systems anonymize data where possible and comply with regulations such as GDPR helps mitigate privacy concerns while maintaining security. Reducing false positives is essential to avoid alert fatigue and ensure the security team can focus on genuine threats. Fine-tuning the UBA system to differentiate between legitimate changes in network traffic patterns and potential threats reduces false positives, allowing the security team to focus on actual security incidents. UBA systems must manage large volumes of data and users without performance degradation. Using scalable cloud-based solutions to manage the high data throughput required for analyzing logs from system log servers and network traffic can help the UBA system remain effective. Analyzing case studies where UBA successfully detected insider threats or prevented data breaches provides practical insights into its application. For example, a financial institution using UBA detected an employee downloading sensitive client information to an external drive after work hours, preventing a potential data breach. Multiple industries utilize UBA to safeguard sensitive information and ensure compliance with regulations. For instance, in healthcare, UBA helps monitor access to patient records through network analysis, while syslog monitoring ensures compliance with legal privacy requirements and detects unauthorized access attempts. In this video, you learn that user behavior analysis involves systematic monitoring and detailed analysis of user actions within a network to identify patterns and anomalies. User behavior analysis concepts include baselining normal behavior, anomaly detection, and contextual awareness. UBA techniques and tools include machine learning algorithms, statistical analysis, and log analysis. Some UBA implementation techniques include data collection, integration with SIEM systems, and continuous monitoring. While implementing UBA, you must remain aware of data privacy concerns, false positives, and scalability. UBA helps safeguard companies across industries and user roles from financial to healthcare. Welcome to Stateless Inspection. After watching this video, you will be able to describe the stateless inspection process, explain an example of stateless inspection, list stateless inspection use cases, and recall the benefits of stateless inspection. Regular routers and some firewalls use stateless inspection, sometimes called stateless filtering, for data packet inspections. The term stateless means that the devices inspect each data packet individually at both the source and destination ports without knowledge of previous packets. Stateless inspections do not maintain a database or session table of the inspected packets. Therefore, there is no record of the packet inspections. Next, learn what happens during packet inspection. First, stateless inspection examines the IP address at the source port. The organization might use an ACL or access control list rule to determine whether a source IP address is allowed into the network or if users can access the destination address. Next, the hardware or software examines the IP address at the destination port to determine whether or not to allow that IP address or service into the network. This process repeats packet by packet, each time with no memory of prior packet inspection or session. Here's an example of a stateless inspection event. When an employee opens their computer's web browser, the browser operates in the network application layer and can create TCP or UDP traffic. However, TCP is the most common protocol traversing the network. Since the packet uses TCP on network layer 4, it will have both the source and destination IP addresses. The packet header contains the source IP address of the client machine and the destination IP address of the receiving computer or web server. Network devices use this information to route packets across different networks and ensure they reach the correct destination. Packet inspection at this layer allows devices to determine the overall path the packet should take. Then, the Layer 2 information joins the packet header. This is information about the local network segment added by the network, such as the physical or MAC address of the source and destination computers and the MAC address of the gateway. The encapsulated packet is sent to the physical layer, either wired or wireless Ethernet. The packet will go to the router, which evaluates it. If the source IP address, in this case the client machine, is allowed to access the server, TCP or UDP traffic is permitted, and the destination port is allowed, then the packet can travel from the server to the server. Now that you are familiar with the stateless inspection process, learn why organizations use stateless inspection. Organizations use stateless inspection to protect routing engine resources, control traffic entering or leaving your organization, aid in troubleshooting, and manage traffic routing through routing instances, such as when a router supports virtualization, allowing you to manage traffic flow from specific sources to specific destinations, and stateless inspection is also useful for performing quality of service, QoS, to prioritize traffic, and class of service, COS, tasks by marking the traffic. Though of another away, what are some benefits of stateless inspection? First, it's faster than stateful inspection. It provides a degree of control over what's allowed in our network and is great for troubleshooting purposes when classifying packets. Let's recap. In this video, you learned that A stateless inspection means that the devices inspect each data packet individually at both the source and destination ports without knowledge of the previous packet. Stateless inspections can happen when a user sends or receives browser data. Organizations use stateless inspections to control traffic going in or out of their organization, perform network troubleshooting, control traffic routing, and perform quality of service and class of service tasks. And stateless inspection is faster than stateful inspection, providing network controls and support for troubleshooting purposes when classifying packets. Welcome to Stateful Inspection. After watching this video, you will be able to discuss stateful inspection, explain the function of stateful inspection with examples. When dealing with network security, the significance of firewalls is paramount. To monitor the state of active network connections and allow smooth flow of network packets without errors, organizations use a firewall technology called the stateful inspection. Also called the dynamic packet filtering, it has the potential to analyze and examine both incoming and outgoing packets. Let's understand this in detail. A stateful inspection means inspecting each packet with knowledge of all other packets that have been sent or received from the same session. A session consists of all the packets exchanged between parties during an exchange. Sessions have several elements like the source IP address, the destination IP address, the source port, the destination port, and in some cases, there's an identifier for the instance if, for example, your router supports virtualization. If the traffic comes from the same IP address and goes to the same destination address, and comes in from the same source port and goes into the same destination port, whether TCP or UDP, the firewall will know that these are from the same session and can automatically allow or discard the packet. You can see in this example that a session ID is assigned. This means that the firewall maintains a database of the session and keeps track of all the packets in the session. You can see some of the information associated with the session, like the session ID and the policy name. You can configure a timeout value so the session won't remain open forever. You can also see the incoming interface, the source IP address, the destination IP address, what VLAN or interface the packet is coming from, and the number of packets and bytes used in the session. If there is any network address translation, you can view that information as well as the outgoing interface. This output is specific to a Juniper firewall. So what happens if you have both a stateless and a stateful inspection? The stateless inspection is performed first, followed by the inspection of the stateful data. Shown here is a diagram that is specific to the Juniper firewall. This is the flow that the packet follows. If you have an incoming packet that matches the session, the firewall evaluates the screen. It analyzes the type of traffic and matches it against a session and applies the required service. Some of the services shown are AppTrack, AppDOS, AppQoS, AppFW, and IDP, which are some of the more advanced security services. If the incoming packet doesn't match an existing session, then it follows a different flow. First, screens are applied. Screens are filters that protect against flow or denial of service attacks. Then, if required, the static is applied, then the destination NAT if it is configured. Finally, the routing and the policy evaluation are conducted. So depending on the incoming and outgoing interfaces that are defined once the route is confirmed, the zones are defined, followed by a policy that will allow or discard the traffic. In some cases, you might see a reverse static NAT. The source NAT is gone after the policy evaluation. When you are a network administrator, this type of flow is good to have in mind. You can then apply the services and build the session. So you can see when an incoming packet doesn't match an existing session, the path through the firewall is longer. Similarly, if the packet matches an existing session, its path is shorter because the firewall already knows what this packet can do. In this video, you learn that stateful inspection or dynamic packet filtering is a firewall technology to ensure smooth flow of network packets. Stateful inspection involves inspecting each packet in a session. A session consists of packets exchanged between parties. Session elements include source IP address, the destination IP address, the source port, the destination port, and an identifier. The stateless inspection is performed before stateful inspection. Welcome to Firewall Filters with Intrusion Systems. After watching this video, you will be able to describe the purpose of firewall filters, identify 3 types of firewall filters, differentiate between intrusion detection system, IDS functions, and intrusion prevention system, IPS functions, and describe how IDS and IPS integrate with firewall filters. Firewall filters serve as gatekeepers, enforcing security policies to regulate inbound and outbound network traffic. Let's check out 3 types of firewalls. Stateless firewalls examine individual data packets based on their packet headers and make filtering decisions without considering packet context. Unlike their stateless counterparts, stateful firewalls monitor the state of active connections, allowing for more nuanced filtering decisions based on connection context. Application-level firewalls operate at the application layer of the OSI model. Application-level firewalls inspect packet payloads, enabling granular control over network traffic based on specific application data. Intrusion detection systems serve as vigilant monitors, continuously scanning network traffic and system activities for signs of suspicious behavior indicative of potential security breaches. You can categorize intrusion detection systems into 2 main types. Network-based IDS, known as NIDS, monitors network-wide traffic patterns, flagging anomalies and potential threats, such as unauthorized access attempts or unusual traffic patterns. Host-based IDS, known as HIDS, monitors individual hosts or devices. HIDS scrutinizes system logs, file modifications, and process activities, providing insight into potential intrusions or unauthorized access attempts at the host level. Intrusion protection systems are like proactive security guards. These systems go beyond detection by actively preventing identified threats from causing harm. Network administrators deploy network-based intrusion protection systems at their network perimeter. The systems scrutinize incoming and outgoing traffic, instantly blocking or neutralizing known threats before they can penetrate the network. In contrast, network administrators install host-based intrusion protection systems directly on individual hosts or devices. These systems monitor system activities in real time, preemptively thwarting malicious actions, such as unauthorized file modifications or malware execution attempts. Next, check out some examples of intrusion systems at work. An intrusion detection system might detect a series of unusual login attempts that match the pattern of a brute force attack. It generates an alert to notify the administrators, but does not take any direct action to stop the login attempts. In contrast, an intrusion prevention system might detect a SQL injection attempt aimed at a web server. Upon detection, the IPS blocks the malicious query before it reaches the server, thereby preventing the attack from succeeding. Intrusion detection systems offer comprehensive monitoring capabilities, providing valuable insights into network and system activities. However, intrusion detection systems can suffer from overload due to the high volume of alerts, including false positive alerts. Intrusion prevention systems provide active threat prevention and immediate response capabilities, bolstering network security. Yet intrusion prevention systems also carry the risk of false positives. They require meticulous configuration to avoid blocking legitimate traffic and effectively balance security and accessibility. When intrusion detection systems coexist with firewalls, the firewall blocks known threats while the system scrutinizes permitted traffic for anomalies. The intrusion detection system alerts administrators to potential security breaches for further investigation and remediation. Conversely, when network administrators integrate intrusion prevention systems with firewalls, the firewall filters incoming traffic. In contrast, the intrusion prevention system actively inspects and neutralizes threats in real time, ensuring an uninterrupted flow of legitimate traffic while preemptively thwarting malicious activities. Firewall filters, IDS, and IPS systems complement each other synergistically, creating a robust defense mechanism against evolving cyber threats. While firewall filters enforce static security policies, IDS and IPS systems add dynamic layers of protection, actively monitoring and preventing potential intrusions or malicious activities. In this video, you learn that firewall filters enforce security policies to regulate inbound and outbound network traffic. Firewall filter types include stateless, stateful, and application-level firewalls. Intrusion detection systems continuously scan network traffic and system activities for signs of suspicious behavior. And while firewall filters enforce static security policies, IDS and IPS systems add dynamic layers of protection, actively monitoring and preventing potential intrusions or malicious activities.
Hello, and welcome to Using Your Windows Lab Workspace. We're excited for you to take these next steps in your skills journey. The labs in this course and other courses provide you with a virtual, hands-on lab environment where you can boost your skills by practicing what you've learned in your course videos and readings. Your lab space, also known as a guided project or the My Cloud Workspace window, contains all the software you need to successfully complete your lab tasks. You'll also open a lab instructions file. For your best experience, we recommend displaying your lab space and instructions side by side. To access your hands-on lab, first open the item in the course for the hands-on lab. If the lab instructions display in a new tab, hover over the tab and pull the tab down onto the desktop. You can drag the window edges to resize the window to about 1/3 of the screen size. You'll return to this window later. Return to the course screen and scroll through the displayed course lab instructions. Select the checkbox to accept the Coursera Honor Code conditions. Then click the Open Tool button. Next, you'll see the Coursera Guided Project window. This window may take a moment to display. The displayed My Cloud Workspace window is divided into two panes. The left pane is named the Cloud Workspace window, and the right pane is named the Instructions window. You won't use this instructions window. Now, you can expand the Cloud Workspace pane on your screen's left side using one of two methods. Drag the vertical slider between the Cloud Workspace and the instructions pane to the far right side of the screen, or click the Expand Cloud Workspace window button displayed on the top right of the left pane. Take a moment to view your lab window. You can click the Lab Window Resolution drop-down arrow to adjust the size of the on-screen icons in the Cloud Workspace. And next, let's adjust your browser windows to see your Cloud Workspace and lab instructions side by side. On the Cloud Workspace lab window, hover over the double box icon located in the top right of the browser window to reduce the size of your window. Move the window to the left side of the screen. Now, drag the window's right edge so that the Cloud Workspace lab window uses about 2/3 of the available desktop space. Next, select the browser window that displays your lab instructions. Drag the instructions window so that the window is to the right of the Cloud Workspace lab window. Now, you can perform the lab tasks in the Cloud Workspace window while using the lab instructions. After completing the lab, select Leave Session to close the Cloud Workspace window, then close your lab instructions using the option available for your browser. Also, before you begin, here's some extra information you need to know. Each time you connect to these labs, Coursera creates a fresh new environment. Data or files you saved in a previous session are no longer available. To avoid losing your data, plan to complete your lab tasks in a single session. These labs are timed to provide enough time to complete lab tasks, but if you leave the lab session unattended, your lab may time out or end. Now, these setup instructions used a Chrome browser within Microsoft Windows 10. Other browsers and web browsers on Mac or Linux computers may use different navigation. You're now lab ready. Let's get started.
Welcome to this video, where you will explore intrusion detection and prevention systems purposes, differences, advantages, and limitations. After watching this video, you will be able to summarize the purpose of intrusion detection systems, IDS, and intrusion prevention systems, IPS, explain the key differences between IDS and IPS, recognize the advantages and limitations of both IDS and IPS, and explain why organizations use both IDS and IPS. An intrusion detection system, or IDS, is a network security technology designed to monitor network traffic for suspicious activities and potential threats. Intrusion detection systems continuously monitor system traffic and activities, Detect and identify anomalies, misuse, or policy violations by comparing traffic against a database of known attack signatures. And notify staff, including administrators or security personnel, of potential threats using alerts or logs. Network-based intrusion detection systems monitor network traffic on specific segments, typically using a dedicated device. In contrast, host-based intrusion detection systems run on individual hosts or devices and monitor system logs, file integrity, and other local activities. An intrusion prevention system, or IPS, builds upon the capabilities of IDS by not only detecting threats, but also taking proactive steps to block or mitigate them, such as dropping malicious packets, blocking offending IP addresses, and resetting connections. Like IDS, IPS monitors and analyzes network traffic to detect suspicious activities. It takes immediate action to block detected threats, thereby preventing potential damage. IPS can modify firewall rules, close vulnerable access points, and initiate other defensive measures. Network-based IPS or NIPS are positioned within the network and can monitor and prevent malicious network activities in real time. In contrast, organizations deploy host-based IPS on individual hosts. They protect the device at the endpoint level by blocking suspicious activities on the device. Understanding the differences between IDS and IPS is crucial for selecting the appropriate system for specific security needs. First, let's examine how you position these systems. Organizations deploy IDS in line to passively monitor network traffic and generate alerts without intervention to prevent real-time attacks. They also deploy IPS to monitor and control network traffic actively. IDS and IPS also have different response mechanisms. Intrusion detection systems alert administrators to suspicious activities, relying on those administrators to take manual action. However, intrusion prevention systems automatically take predefined actions to block or mitigate threats without human intervention. IDS have minimal impact on network performance because they operate out of band, whereas IPS potentially impacts network performance as it inspects and filters all traffic in line. An IDS is suitable when prioritizing, detecting, and analyzing threats. Immediate prevention is not critical. An IPS is ideal for environments requiring real-time threat interception and automatic responses to attacks. Intrusion detection systems offer detailed analysis and alerts for potential threats to forensic analysis and compliance reporting with minimal impact on network performance. However, these systems can generate many false positives, do not have automatic prevention capabilities, and require significant human intervention. Intrusion prevention systems offer real-time threat prevention and mitigation, automated responses that reduce workload for security personnel, and enhance network security by immediately blocking known threats. However, intrusion prevention systems can impact network performance due to inline deployment. They can report false positives that result in blocking legitimate traffic. And finally, they require careful configuration and tuning to balance security and performance. Both IDS and IPS are integral components of a comprehensive network security strategy. IDS excels in monitoring and alerting, providing valuable insights and forensic data, while IPS offers real-time protection by actively blocking threats. Together, they provide a layered defense approach, enhancing an organization's security posture. In this video, you learn that IDS monitors network traffic for suspicious activities and potential threats and generates alerts, while IPS uses predefined actions to prevent attacks. IDS systems have little to no impact on the network, and IPS can affect network performance. IDS provides detailed analysis and alerts, but can generate false positives and, without automatic interception capabilities, require human intervention. IPS provides real-time threat prevention and mitigation, but can impact network performance and report false positives. And both IDS and IPS are part of a layered defense. Welcome to Network Address Translation. After watching this video, you will be able to explain the concept of Network Address Translation, referred to as NAT. Describe why NAT is used in networking, and identify 3 NAT types, their uses and challenges. Network Address Translation, NAT, provides an extra security layer between private and public networks. A traffic routing device, such as a router, is an intermediary between the local, private network and the public internet. For outbound data, NAT modifies the network address information in the IP header of packets, masking the internal IP address from external networks while data is in transit across a traffic routing device. In doing so, NAT helps manage the shortage of IPv4 addresses. NAT translates the public IP address back to the private IP address for inbound data, ensuring that the data reaches the correct device within the local network. NAT allows multiple devices on a local network to be mapped to a single public IP address. This IP address conservation reduces the need for a unique IP address for each device, which is particularly important given the limited availability of IPv4 addresses. Next, NAT provides a layer of security against external threats by hiding internal IP addresses. External devices can only see the public IP address, not the internal IP addresses of the devices on the local network. NAT provides simplified network management, making it easier to manage IP addresses within a local framework. Network administrators can use a private range of IP addresses within the local network and only need to manage the public IP addresses at the network's edge. Static NAT maps one private IP address to one public IP address. This is useful for devices that need to be accessible from outside the network, such as a web server. For example, if an internal web server has the private IP address 192.168.1.10, static NAT can map it to a public IP address such as 203.0.113.5, making the server accessible from the Internet. Dynamic NAT maps a private IP address to a public IP address from a pool of public addresses. It is useful when multiple devices need to access the Internet, but each session does not require a fixed public IP address. For instance, if multiple devices in an office, such as a phone system and 3 printers, need Internet access, Dynamic NAT can assign available public IP addresses from a pool to each device as needed. Port Address Translation, or PAT, is also known as NAT overload. PAT maps multiple private IP addresses to one public IP address, but with a different port number for each session. This is the most common form of NAT used in home networks. For example, suppose multiple devices in a home network, such as 192.168.1.2 and 192.168.1.3, are accessing the Internet. In that case, PAT allows all the devices to share a single public IP address by assigning different port numbers to each device's session. Next, explore some practical applications of using NAT. You might find NAT implemented as static NAT in a home network, or you might see NAT implemented as PAT. For example, a home has a laptop with a tablet with internal IP addresses such as 192.168.1.2 and 192.168.1.3. The router maps these devices to a single public IP, 203.0.113.5, using different port numbers for each session. For instance, if 2 devices initiate connections, the router might assign ports 10,001 and 10,002 to the outgoing connections. This allows both devices to share the same public IP address while maintaining distinct sessions. You'll also find NAT in use with outgoing private network traffic. For example, a small business with an internal web server has a private IP address that must be accessible from the Internet. The server's external-facing NAT, 203.0.113.6, maps to the internal IP address 192.168.1.10. External users who access the web server use the public IP address 203.0.113.6. Another common issue is port forwarding misconfiguration. Port forwarding misconfiguration results in services that are inaccessible from outside the network. For example, if a game server on the internal network is not correctly port forwarded, external players cannot connect. Lastly, IP address conflicts from overlapping IP address ranges between internal and external networks can cause connectivity issues. For instance, routing issues can happen if 2 networks use the same private internal IP address range. For example, suppose a company has 2 separate locations, with servers with identical IP addresses of 192.168.1.10. In that case, the routers cannot correctly route the employees' computers to the correct server. NAT introduces some delay in processing data packets because the router needs to translate the IP addresses. In high-traffic networks, this can lead to performance degradation. Additionally, NAT can complicate protocols that embed IP address information within the payload, such as session initiation protocols, called SIPs, used in voice-over IP applications. In this video, you learn that network address translation modifies IP address information in packet headers to mask internal IP addresses for outbound data, and translates public IP addresses back to private addresses for inbound data. NAT provides a layer of security against external threats by hiding internal IP addresses. Static NAT, dynamic NAT, and port address translation, PAT, are three types of network address translations. You can use NAT to mask internal IP addresses for devices sending and receiving data, and for devices on networks that need to share IP addresses but use different ports. And common NAT issues include port forwarding problems, IP address conflicts, and performance overhead. Welcome to File Integrity Monitoring. After watching this video, you will be able to describe the concept and importance of File Integrity Monitoring, FIM, in cybersecurity, identify critical components and processes involved in FIM, and describe the role of FIM within broader network security strategies. File Integrity Monitoring, or FIM, is a vital cybersecurity process. FIM continuously verifies the integrity of operating system and application software files by comparing those files to a trusted baseline. Any deviations from the baseline are flagged as potential security concerns. This monitoring is crucial for maintaining system security and quickly detecting unauthorized changes that may indicate breaches or malicious activity. Ensuring that essential files have not been tampered with is vital for maintaining the operational integrity of both system and application software. Unauthorized changes to essential files can lead to significant security vulnerabilities. FIM helps promptly identify unauthorized file modifications, indicating security breaches, malware infections, or insider threats. By identifying these changes quickly, organizations can take immediate action to mitigate potential damage. Many regulatory standards, such as PCI DSS, HIPAA, and SOX, mandate using FIM to ensure that organizations maintain the integrity and security of sensitive data. Compliance with these standards is a legal requirement and helps build trust with clients and stakeholders. Core components and processes for file integrity monitoring include establishing a reliable file system baseline as a reference point for detecting changes. Establishing a baseline involves capturing the state of files at a specific time, creating a reference for future comparisons. Depending on the organization's requirements, you can use monitoring and detection mechanisms continuously, in real time, or periodically at scheduled intervals to check files against the baseline and detect any modifications. These systems provide alerting and reporting that notifies administrators of detected changes and provides detailed reports for analysis and action. You can configure alerts to notify administrators via email, SMS, or other communication channels. FIMs monitor system, configuration, application, and user data files. System files are essential operating system files critical for the system's functionality and security. Unauthorized changes to these files can significantly impact system performance and security. Configuration files determine the settings and behavior of both system and application software. Unauthorized changes to configuration files can lead to misconfigurations, making the system vulnerable to attacks. Application files include executable files and associated resources necessary for running applications. Protecting application files ensures that the software functions correctly and securely. And finally, user data files are essential data files used by applications that may contain sensitive information. Monitoring these files helps protect user data and ensures compliance with data protection regulations. The process involved in file integrity monitoring include capturing the initial state of files to set a baseline, implementing scheduled scans or real-time monitoring, and configuring alerts to generate comprehensive reports. These processes are crucial for effective file integrity management. Next, learn about the 3 essential steps to implement file integrity monitoring. When you install your FIM tools, you'll first want to define your scope of monitoring and establish your baselines. Begin with an initial file state capture. This process involves taking a snapshot of the current state of all files to create a baseline. This snapshot serves as the reference point for future file state comparisons. Next, select your hashing techniques. FIMs use hashing algorithms, such as MD5, SHA-1 and SHA-256, to create unique file identifiers. These hashes help accurately detect file changes. Each file's hash value is compared against its baseline hash to detect alterations. Monitoring is a significant component of FIMS. Determine whether your system will perform scheduled scans or continuous real-time monitoring. Scheduled scans occur regularly, while real-time monitoring constantly checks files for changes. Both methods have advantages, with real-time monitoring providing immediate detection of changes and scheduled scans offering a more controlled and resource-efficient approach. Then, set the parameters to detect file modifications, additions, and deletions. FIM systems identify any changes, whether modifications to existing files, additions of new files, or deletions, by comparing the current state to the baseline. These changes are then flagged for further investigation. Next, determine how you will respond to integrity violations. Managing integrity violations involves identifying legitimate changes versus potential threats, allowing authorized modifications to minimize false alarms, and investigating unauthorized changes to respond effectively. These actions help maintain the integrity and security of the system. First, investigate all unauthorized changes and thoroughly examine suspicious modifications to understand their cause and impact. This may involve collaboration with other security teams and using additional tools to trace the source of the changes. Next, restore files from backups. If necessary, revert to previous versions of files and use backups to restore the system's integrity. Ensuring backup procedures are reliable and regularly tested is crucial for effective recovery. Finally, mitigate the existing security breaches by taking steps to secure the system after a detected breach, including patching vulnerabilities and enhancing security measures. This may involve implementing additional controls, updating policies, and thoroughly reviewing the incident to prevent future occurrences. File integrity monitoring complements other security measures, such as firewalls and antivirus solutions, to provide a robust defense strategy. FIM also ensures compliance with regulatory requirements through regular audits and reviews, maintaining the efficiency of the overall network security strategy. Many regulatory standards mandate the use of file integrity monitoring, FIM. Organizations must ensure that their FIM practices meet these compliance criteria to avoid penalties and remain compliant. Regular audits and reviews of FIM policies and procedures are essential for maintaining compliance and ensuring the effectiveness of the FIM system. In this video, you learn that file integrity monitoring is crucial for maintaining system security and quickly detecting unauthorized changes that may indicate breaches or malicious activity. Core components and processes for FIM include establishing a reliable file system baseline, monitoring file integrity, providing reports, and maintaining the system. And file integrity monitoring complements other security measures, such as firewalls and antivirus solutions, to provide a robust defense strategy. Welcome to Data Loss Prevention. After watching this video, you will be able to discuss the importance of data loss prevention, DLP, in cybersecurity, list the key components and technologies of DLP, and describe how to implement DLP strategies. One of the most common challenges organizations face today is the threat of data breaches resulting in the loss of sensitive information. This impacts their finances and reputation heavily. To survive this, organizations use a set of tools and processes to monitor, detect, and block unauthorized data transfers, ensuring that data in use, in motion, or at rest is protected, thus protecting their valuable information from internal and external threats. This process is referred to as data loss prevention, or DLP. Let us now discuss the advantages of DLP in cybersecurity. DLP safeguards confidential data, such as intellectual property, financial information, and personal data, ensuring its integrity and confidentiality. By protecting sensitive data, DLP ensures compliance with regulatory standards like GDPR, HIPAA, and PCI DSS. DLP detects and blocks unauthorized data transfers, reducing the risk of data breaches. Let's discuss the core functions of DLP. DLP solutions classify data based on sensitivity and importance, identifying and tagging sensitive information like personal data, financial records, and intellectual property. Additionally, It plays a pivotal role in creating and executing policies that comply with regulatory standards for handling sensitive data. These policies define who can access data and under what conditions. To perform these functions, DLP uses a range of technologies. Let's discuss them. To analyze files and content to identify sensitive information, DLP inspects emails, documents, and other data for patterns that match the predefined policies. Similarly, to evaluate the context of data usage and to ensure it aligns with established policies, DLP analyzes user behavior, device types, and network activities. DLP also plays a pivotal role in protecting data in transit and at rest with encryption. It uses tokens to replace sensitive data with unique identifiers to build up defenses against attacks. Let's now discuss how you can implement DLP for your organization. First, assess the data security needs of your organization. To do so, identify sensitive data types and potential risks. Next, deploy DLP solutions using tools into existing network infrastructure to monitor and protect sensitive data. Additionally, define and execute DLP policies based on regulatory requirements to make them compliant with global standards. Finally, conduct training sessions on data protection and compliance to raise employee awareness. With all this said, sometimes the attackers penetrate through the responses. In such cases, threat identification and remediation are crucial. Let's discuss how you can respond to these threats. First, use DLP tools to detect data leakage incidents in real time by analyzing alerts and logs. Develop and implement clear incident response procedures to identify the source, contain damage, and take corrective actions promptly. Isolate affected systems immediately to prevent further data loss and protect other systems. Conduct investigations to analyze the cause and impact of incidents. Implement corrective actions by updating policies, enhancing security measures, and providing additional training to prevent future incidents. In this video, you learn that DLP tools prevent unauthorized access and ensure data integrity for sensitive information. They monitor and block unauthorized data transfers across all data states. DLP ensures compliance with GDPR, HIPAA, and PCI DSS, reducing data breach risks. Core DLP elements include data classification, policy enforcement, and continuous monitoring. And DLP technologies analyze content, evaluate context, and use encryption for data protection. Welcome to Network Access Control, or NAC. After watching this video, you will be able to discuss the significance of Network Access Control, NAC, in cybersecurity, list the key components and technologies involved in NAC, analyze the role of NAC within broader network security strategies. For any organization, securing data against attacks and threats is of prime importance. Most of these threats arise from weak rules and authentication policies that allow anyone to access the network, which attackers take advantage of. And so, it is crucial to assess the rules associated with access permissions. Network Access Control, or NAC, helps restrict users and devices based on the organization's requirements, just like doors and windows keep physical intruders from attacking physical assets. Let's take a deeper look into NAC. NAC is a security solution that enforces rule-based controls over devices and users attempting to access network resources. NAC systems are designed to verify the identity and security posture of devices before granting them access to the network to ensure overall security. Let's discuss a few advantages of NAC. NAC helps prevent unauthorized devices from accessing the network, thus reducing the risk of attacks. NAC ensures that devices comply with security policies and organizational rules regarding access controls, such as keeping antivirus software and firewalls up to date, which helps to stop unauthorized access.
By verifying the security posture of devices,
NAC reduces the risk of malware infections and cyber attacks, thus ensuring overall network security. Let's look at the key components of NAC. Within NAC, authentication, authorization, and compliance enforcement play a crucial role in managing access control. Authentication involves the use of credentials, usernames, passwords, and biometric data to verify the user's identity and grant access.
Authentication works on credential verification against the authentication server and then uses digital certificates to verify the identity of users and devices. Authorization, on the other hand, determines the level of access granted to authenticated users and devices based on their role and predefined policies.
Authorization works on policy enforcement and RBAC, role-based access control, to control who can access what data. Lastly, compliance enforcement ensures that the devices requesting access meet security requirements. This includes regular assessments of devices and remediation using necessary updates and security patches. Let's now discuss the steps to implement NAC. 1. Evaluate the existing network infrastructure, devices, and security policies to identify integration points for NAC solutions. 2. Install and configure NAC components, such as authentication servers, policy servers, and enforcement points, and integrate NAC solutions with the existing network infrastructure. 3. Create access control policies based on user roles, device types, and compliance requirements. 4. Lastly, conduct periodic testing to ensure that NAC policies are performing well and do not inadvertently block legitimate access.
While these processes help to manage threats, there are unfortunate events where an attacker manages to penetrate the network. How do you respond in such cases?
NAC offers ways to identify, handle, and remediate any violations by 1.
Continuously monitoring network access attempts and generating real-time alerts for suspicious activities.
2. Developing and implementing incident response procedures for access control violations, including identifying sources, containing threats, and taking corrective measures to prevent future incidents. 3. Placing non-compliant devices in a quarantine network for remediation, ensuring they don't risk the main network. 4. And implementing automated remediation to quickly address non-compliance and restore network access for legitimate users. It is now imperative that integrating NAC into network security has many advantages. Let's define a few strategies to do so. 1.
NAC complements firewalls,
IDS, and antivirus software, adding protection by controlling network access based on device and user compliance. 2. NAC monitors the devices and users, aiding in threat identification and efficient policy enforcement. 3. NAC enforces access control policies, helping organizations meet regulatory standards and ensure compliance. In this video, you learn that Network Access Control, NAC, ensures that only authorized devices access network resources, reducing security risks. NAC verifies device compliance with security policies, like antivirus updates and enhanced network protection. Implementation involves deploying NAC components, defining access policies, and testing for effective security enforcement. NAC responds to violations by monitoring, isolating non-compliant devices, and automating remediation processes. Integrated with firewalls and antivirus, NAC strengthens network security and meets regulatory compliance standards.
Welcome to Endpoint Detection and Response. After watching this video, you will be able to define Endpoint Detection and Response, known as EDR, describe why EDR is important in cybersecurity, list the key components and processes of EDR systems, explain how to integrate EDR, and explain how EDR fits into network and compliance practices. Endpoint Detection and Response, or EDR, is a set of cybersecurity tools and practices designed to detect, investigate, and respond to suspicious activities on endpoints, such as desktops, laptops, servers, and mobile devices. EDR solutions provide continuous monitoring and analysis of endpoint activities to identify and mitigate potential security threats in real time. EDR solutions fit into the cybersecurity stack by providing detailed visibility into endpoint activities, enabling security teams to detect and respond to threats more effectively, reducing the potential damage from security incidents. EDR solutions continuously collect data from lightweight agents on endpoints, monitoring system activities such as logs, process information, file activities, network connections, and user behaviors. The system analyzes this data by aggregating and correlating data from multiple endpoints to identify patterns and anomalies, detecting coordinated attacks and other security threats. EDR systems apply threat detection techniques, including signature-based detection, heuristic analysis, and behavioral analysis to identify malicious activities on endpoints. Heuristic analysis uses predefined rules to detect suspicious activities, while anomaly detection identifies deviations from standard behavior patterns. Signature-based detection compares endpoint activities with a database of known malware signatures. When a potential threat is detected, EDR tools provide capabilities for investigation and analysis using root cause analysis, timeline reconstruction, and automated event correlation. Timeline analysis reconstructs the sequence of events leading to the detection, while root cause analysis identifies the origin of the threat. EDR solutions support rapid response and remediation by enabling security teams to isolate compromised endpoints, terminate malicious processes, and apply security patches. Automated response actions help to quickly contain and mitigate threats, while manual forensic analysis and evidence collection allow for thorough investigation and remediation measures. To accomplish these capabilities, EDR systems also use behavior analysis, machine learning algorithms, and forensic analysis. Behavioral analysis supports monitoring and analyzing endpoint behaviors to detect deviations from normal patterns. This technique helps identify previously unknown threats by recognizing suspicious activities. EDR systems implement machine learning algorithms to analyze large datasets to identify patterns and anomalies associated with malicious activities. These algorithms improve over time, enhancing the accuracy of threat detection. Forensic analysis tools within EDR solutions allow security teams to conduct detailed examinations of compromised endpoints, including file system analysis, memory dumps, and network traffic captures. Next, use the following high-level steps as a guide for EDR implementation. Implementing EDR begins by performing the assessment and planning tasks necessary to evaluate the organization's endpoint security needs and select an appropriate EDR solution. Plan your deployment strategy, including integrating existing security infrastructure and defining security policies. Next, install, configure, and deploy EDR agents on all endpoints. Remember to verify that the deployed agents function correctly, including communicating with the central EDR system. Then, define security policies and rules within the EDR solution. Set up detection rules, response actions, and alerting mechanisms. When installing the EDR system, implement the process and monitor endpoint activities continuously and routinely. Review alerts regularly, investigate incidents, and update detection rules and policies as needed. Now, learn about responding to security incidents. First, use the available EDR tools, including alerts and logs, to identify unauthorized activities in real time and determine the scope of the incident. Next, respond to incidents by identifying their source and containing potential damage. Then, perform remediation and recovery tasks to prevent further damage. Begin by isolating the affected systems to prevent further data loss or damage. Next, conduct thorough investigations to understand the cause and impact of security incidents. This involves analyzing logs, interviewing stakeholders, and reviewing policies to identify vulnerabilities and weaknesses. Finally, implement corrective actions to address the root cause of incidents and prevent future occurrences. This includes updating EDR policies, enhancing security measures, and conducting additional employee training. EDR systems complement security measures such as firewalls, intrusion detection systems, and encryption to provide a comprehensive data protection strategy. By preventing data loss, EDR adds an additional layer of security to the organization's overall defense strategy. Many regulatory standards require organizations to implement measures to protect sensitive data. EDR provides the required visibility and control of data activities to enforce data protection policies. This visibility is crucial for compliance with legal and regulatory security standards and maintaining customer and stakeholder trust. In this video, you learn that Endpoint Detection and Response, EDR, is a set of cybersecurity tools and practices for detecting, investigating, and responding to suspicious activities on desktops, laptops, servers, and mobile devices. EDR provides detailed visibility and advanced detection techniques, enabling security teams to quickly identify, contain, and respond to sophisticated threats more effectively. Key EDR components and processes include data collection, data analysis, threat detection, investigation and related analysis, and response and remediation. To integrate EDR, evaluate the organization's endpoint security needs, deploy the EDR agents, define security policies and rules, and monitor and manage the system. EDR is one part of a comprehensive data protection strategy, and EDR provides detailed visibility and control into data activities required for compliance with legal and regulatory security standards. Welcome to Extended Detection and Response. After watching this video, you will be able to define extended detection and response, describe the significance of extended detection and response for cybersecurity, list key capabilities, recall the implementation steps, explain how extended detection and response integrate into the network security strategy, and explain how extended detection and response support regulatory requirements. Unlike traditional security solutions that operate in silos, Extended Detection and Response, XDR, are platforms that extend endpoint detection and response capabilities by incorporating information from a broader range of security tools, such as network traffic analysis, cloud security, and email security solutions. XDR provides a centralized platform that unifies security alerts and responses from multiple security tools. This single platform reduces complexity, streamlines workflows, and improves the efficiency of security operations. By correlating data from diverse sources, XDR can detect sophisticated threats that may go unnoticed by individual security products. This comprehensive view helps identify multi-vector attacks and complex threat patterns. With XDR, security teams can access richer contextual information and broader threat visibility, which facilitates faster, more accurate incident response, minimizing the potential impact of security incidents. XDR solutions continuously collect and aggregate data from various security tools, including endpoint detection and response, network traffic analysis, cloud security, and email security solutions. This aggregated data forms a comprehensive dataset for analysis. XDR platforms apply advanced analytics, machine learning, and artificial intelligence to correlate data from different sources. This correlation helps identify patterns and anomalies that signify potential security threats. XDR platforms utilize detection techniques, including signature-based detection, behavioral analysis, and threat intelligence, to identify known and unknown threats. These platforms offer tools for in-depth investigation and forensic analysis. Security teams can analyze incidents comprehensively, understanding threat scope, impact, and root cause. XDR solutions support automated response actions, such as isolating compromised systems, blocking malicious network traffic, and swiftly applying security patches to mitigate threats. Behavioral analysis involves monitoring endpoint and network behaviors to detect deviations from regular activity. Behavioral analysis helps identify zero-day and advanced persistent threats. In addition, machine learning algorithms and artificial intelligence enhance threat detection accuracy by analyzing large data sets. They can also identify patterns and anomalies associated with malicious activities. Machine learning algorithms also adapt over time, improving their effectiveness. Integrating threat intelligence into extended detection and response keeps the system updated with the latest threat indicators and attack techniques, improving its ability to detect emerging threats. During the implementation process, you'll evaluate the organization's security needs and existing resources, including security tools, to determine the appropriate XDR solution. Then, you'll plan the deployment strategy, including integration with current security infrastructure and defining security policies. Next, deploy the XDR platform, configure data collection agents across endpoints, network devices, cloud services, and email systems, and verify that the agents are correctly installed and communicate with the central XDR system. Then, define security policies and detection rules within the XDR platform, tailored to the organization's specific security requirements. This process includes setting up detection thresholds, response actions, and alerting mechanisms. Finally, the organization must continuously monitor its security posture using the XDR platform. As part of the team, you'll regularly review alerts, investigate incidents, and update detection rules and policies to adapt to evolving threats. The organization must also train security teams to use the XDR solution effectively, including threat detection, investigation, and response procedures. Organizations use XDR tools such as data correlation and advanced analytics to identify suspicious activities and potential threats. Procedures for responding to security incidents include containment, eradication, and recovery. Let's learn more about how these respond to security incidents. After a security event, XDR platforms help compromise systems to prevent the further spread of threats and minimize their impact on the organization. The XDR platform supports thorough investigations to determine the root causes and impacts of security incidents. Analyzing logs, timelines, and forensic data from multiple sources helps speed up understanding how the incident occurred and what data or systems were affected. Apply necessary fixes and improvements, including patching vulnerabilities, updating security policies, and enhancing security measures to address the weaknesses identified during the investigation. With its combined capabilities, XDR platforms provide detailed visibility into security events across the entire IT environment. This visibility helps security teams detect and respond to threats more effectively, ensuring better control over the organization's security. Many regulatory standards require organizations to implement measures to protect sensitive data. XDR helps organizations meet these requirements by providing detailed logs, reports, and audit trails of security events and responses. This is essential for avoiding legal repercussions and maintaining trust with customers and stakeholders. In this video, you learn that extended detection and response platforms extend endpoint detection and response capabilities by incorporating information from a broader range of security tools. XDR integration capabilities improve threat detection, leading to faster investigations and incident response times by the organization's IT environment. Key XDR capabilities include data aggregation, correlation and analysis, threat detection, investigation, forensics, and automated responses. To implement the XDR platform, assess the organization's needs and resources, plan the deployment strategy, deploy and configure the platform, define and configure policies, and continuously monitor and manage the platform. Network integration capabilities complement other security measures and enhance visibility and control. And XDR platforms help organizations avoid legal repercussions and maintain customer and stakeholder trust by providing detailed logs, reports, audit trails, and security event documentation.